Hello, and welcome to Sleep Gravity. Tonight, allow the familiar measures of time to slowly fade into the background until minutes, hours, and years no longer need to be counted, because the journey ahead will carry us across spans of time older than mountains, oceans, and even the sun that shines upon Earth. You do not need to remember the enormous numbers, nor do you need to fully imagine every distance that will appear in this story. Simply let your thoughts drift gently, like a thin cloud moving across the night sky, in no hurry, and with no need to know exactly where it will come to rest. Imagine before you a vast, elevated landscape, where rolling hills stretch toward the horizon, the air is clear, and the glow of distant cities is too faint to wash out the sky. Above, countless stars rest quietly in the darkness. Some are bright enough for the eye to notice immediately, while others are so faint that they appear only when you soften your gaze, as though they have always been there, but never wished to draw too much attention to themselves. The light from those stars has crossed regions of space with no wind, no sound, and no footprints of any kind. Sometimes it has taken tens, hundreds, or even thousands of years to reach Earth. When a ray of light first began its journey from its star, the people living on this planet may not yet have built the cities we now consider ancient. And yet, after traveling for so long through space, that light can still touch our atmosphere, pass into the eyes of someone looking upward, and become a tiny point of brightness in the night. Perhaps because stars change so slowly, they often give us a sense of stability. The sky once guided ships across oceans, marked the return of the seasons, and helped people find their way when the land around them no longer offered anything familiar. Constellations seen by people long ago can still be recognized today, making it easy to imagine that the sky is a finished picture and that the stars will continue shining forever, just as they shine tonight. But cosmic time moves to a very different rhythm, far slower than the rhythm of human life. A human lifetime is long enough to witness many changes, but to a star, that entire span is little more than a tiny movement, one that leaves almost no visible trace. Stars are changing every day as well. Their changes simply unfold so quietly that the sky before us appears completely still. Every star began within a cold cloud of gas and dust, drifting through space. Under the pull of gravity, matter was slowly drawn together, much like many small streams flowing toward the same low valley. The cloud became denser, its center grew warmer, and then hotter still, in a process that could continue across immense stretches of time. When the temperature and pressure at the center reached the right threshold, matter began releasing energy, and from within the darkness, a new star gradually emerged. Inside it, a delicate yet enduring balance took shape. Gravity continually pulled the layers of matter inward, while energy produced in the core supported them from within. Because of this balance, a star can maintain its form and continue shining for millions, billions, or even trillions of years. But not every star experiences time in the same way. Some stars are enormous and intensely hot, shining so brightly that they can cause nearby clouds of gas to glow. Yet the high temperatures in their cores also force them to consume their fuel very quickly. They may outshine every neighboring star, but their lives are far shorter than those of smaller, quieter sources of light. In other regions of the galaxy, there are stars smaller than the sun, cooler and so faint that we sometimes need sensitive telescopes to see them. They do not release light with the same intensity, but neither do they hurry through the fuel within them. If massive stars are like brilliant flames burning in the night, then small stars are more like warm embers hidden beneath a layer of ash. They do not illuminate all of space, but they can preserve their warmth for a far longer time. This is one of the gentle truths that nature quietly repeats. What lasts the longest is not always what is largest or brightest. Sometimes, it is simply what changes more slowly and uses what it has in a steadier way. At this moment, we are living in an age when the universe is still filled with light. Clouds of gas are still collapsing to form new generations of stars. Young stars are only beginning to shine, while older stars are slowly moving into different stages of their existence. The sky is not a motionless picture, but a very brief moment in a much longer story, and we happen to be here while galaxies still contain billions of sources of light. But if we could allow time to move faster, carrying us beyond billions and then trillions of years, that view would gradually change, not through a single event unfolding in an instant, but through countless small changes following one after another. The largest stars would complete their lives first. Stars like the Sun would also pass through their own stages, while smaller stars continued to exist in silence. New stars would keep forming for a very long time, but the process would slowly become less common as galaxies aged and suitable supplies of gas grew less abundant. And through all of these changes, the smallest stars could continue to shine, quietly transforming fuel within their cores across spans of time far longer than the current age of the universe. Perhaps, in a future so distant that none of the constellations resemble the sky we know today, a small star will still be shining. It does not need to be the most beautiful star, nor the most powerful. Its light may be nothing more than a faint red glow surrounding a tiny celestial body, yet, in a universe that has grown very old and very quiet, that modest source of light becomes extraordinary simply because it continues. The star does not know that it has outlasted the others. It does not count the years that have passed, nor does it wait for anything still to come. It simply exists in the way the laws of nature allow gravity holding its matter together, slow transformations within its core, producing energy, and a small amount of light continuing to spread into the surrounding darkness. When we think about the last star, there is no need to imagine something heavy or sorrowful. It may be better understood as a story of endurance, of how a small source of light can persist across spans of time so immense that all sense of urgency has long since lost its meaning. And perhaps this journey should begin not with the moment when the light finally disappears, but with a gentler question. Why do some stars exist only for a short time, while others can continue shining longer than almost anything else that has ever appeared in the universe? To find the source of light that may endure the longest, we must first look at the balance that keeps a star alive, the way it uses the fuel within its core, and the reason the brightest stars are sometimes the first to vanish from the sky. To find the source of light that may endure the longest, we must first look at the balance that keeps a star alive, the way it uses the fuel within it, and the reason light, no matter how persistent, is always part of a process, slowly moving forward. A star does not emerge from a point of light that already exists in space. Before it begins to shine, it is part of an immense cloud of cold, diffuse gas drifting among older stars in the galaxy. These clouds are made mostly of hydrogen, along with smaller amounts of helium and traces of heavier elements formed by earlier generations of stars. From a distance, they may appear as dim, dark regions between the glowing bands of the galaxy. Yet each cloud contains an enormous amount of matter spread across distances, so vast that even light may take years to travel from one side to the other. For much of the time, the material within the cloud moves slowly, colliding gently and drifting through complex currents of gas. In some regions, however, the density may be slightly greater than in the surrounding space. That initial difference can be very small, but gravity does not need much of an imbalance to begin its work. Wherever there is more matter, the gravitational pull becomes a little stronger, and that stronger pull draws in even more material. Over time, a small region of the cloud grows denser and continues attracting nearby layers of gas, much like a shallow depression in a sheet of fabric, causing surrounding particles to roll gradually toward the same point. This collapse does not take place within perfectly still matter. Atoms and molecules are constantly colliding, moving chaotically, and exchanging energy. As the cloud is compressed into a smaller volume, the motion within it becomes faster, the temperature begins to rise, and the central region grows increasingly dense and hot. Some of the material may orbit the forming core, creating a broad disk where planets, asteroids, and many smaller objects may later emerge. But at the center of the system, most of the mass continues gathering into a contracting sphere, a protostar that is not yet shining through nuclear fusion, but has already begun releasing heat through gravitational contraction. During this stage, the future star is still being assembled. Matter falls inward from the surrounding cloud, strikes the surface, and adds more energy. Gravity continues pressing the layers of gas toward the center, steadily increasing the pressure and temperature in the core. If enough mass accumulates, the core eventually reaches temperatures of millions of degrees, where hydrogen nuclei move fast enough to partially overcome the electrical repulsion between them and draw close together. Hydrogen is the simplest and most abundant element in the universe. Most hydrogen atoms contain only a single proton in their nucleus. Under ordinary conditions on Earth, two positively charged protons repel one another, so they do not easily combine. But inside the core of a star, the density is extremely high, the pressure is immense, and particles move at extraordinary speeds. After countless collisions, some particles come close enough for the strong nuclear force to take effect, binding them together and beginning the chain of reactions that transforms hydrogen into helium. This is the moment when a star truly enters the most stable period of its life. The energy released in the core does not immediately travel outward as the visible light we see. It must first make an extraordinarily long journey, repeatedly being absorbed, emitted, scattered, and transferred through dense layers of matter. A photon created near the core may take thousands, tens of thousands, or perhaps even longer to find its way toward the surface. Throughout that journey, its energy changes many times until it finally escapes the star as visible light, infrared radiation, or another form of electromagnetic energy. Once the light leaves the surface, it begins the part of its journey that is more familiar to us, traveling through space at the speed of light and perhaps continuing for many years before reaching a planet, a cloud of gas, or a telescope pointed in its direction. But most of the story of that energy began long before it left the star, in a region so deep that no instrument can observe it directly. Inside a star, nuclear fusion does more than create light. It also helps the star resist its own gravity. Every particle of matter within the star is pulled toward the center, and without anything to oppose that force, the entire sphere of gas would continue collapsing into an increasingly small and dense state. Yet the high temperature in the core keeps the matter in vigorous motion, while the outward flow of energy creates pressure that supports the layers above. These two opposing tendencies produce what astronomers call hydrostatic equilibrium. A star can be imagined as a structure held steady from both directions. Gravity pulls inward, while gas pressure and radiation push outward. When these forces reach a balance, the star's size does not change rapidly. The core maintains a suitable temperature, and energy continues to be produced at a relatively steady rate. The star is never completely still. Within it, matter is always flowing, regions of different temperatures are constantly shifting, and tiny oscillations move through its interior. But on a human timescale, this state can last so long that nothing seems to change at all. Our sun is currently in such a stage. Every second, an enormous amount of hydrogen in its core is converted into helium, while a very small portion of its mass is transformed into energy through the relationship between mass and energy described by modern physics. Only a tiny fraction of that energy reaches Earth, yet it is enough to warm the planet's surface, drive the climate, power photosynthesis, and indirectly sustain nearly every ecosystem we know. Daylight, the warmth on our skin, the wind moving across the surface of the sea, and the energy stored within plants all trace their distant origins to reactions taking place deep inside a core we can never see directly. In that sense, every morning is also a familiar expression of the same process unfolding within billions of other stars, across vastly different distances and under very different conditions. Yet this balance is not a clock that can keep running forever without change. The hydrogen in the core is gradually transformed into helium, and helium, being heavier, does not take part as easily in the same kind of reaction at the core's current temperature. Over time, the chemical composition of the central region changes, its density increases, and the way the star transports energy slowly begins to shift. These changes unfold so gradually that, over 1,000,000 years, the star may appear almost unchanged from the outside. But as billions of years accumulate, they eventually carry the star into a new stage of its life. One of the most important things to understand about stars is that they do not use all of their hydrogen at once. Nuclear fusion occurs most strongly only in regions where the temperature and pressure are high enough, mainly near the center. In the outer layers, large amounts of hydrogen may still remain, but that material is not always carried inward to the core, where it can become fuel. This means that a star may contain an enormous amount of matter, while directly using only a portion of it during its first long, stable phase. As the amount of hydrogen in the core declines, the energy being produced is no longer generated in quite the same way as before. Gravity continues to pull inward, causing the central region to contract slightly. That contraction raises the temperature, and the higher temperature can make the remaining reactions proceed more rapidly. From the outside, the star may gradually become brighter even as its central supply of hydrogen is being depleted. This is a subtle change. A star does not necessarily begin to fade as soon as it grows older, because the evolution taking place within it can temporarily cause it to release even more energy. The sun today is brighter than it was when it first entered its stable phase billions of years ago. The change has been extremely slow, but it reveals that the life of a star is not simply the story of a steady lamp growing dimmer with time. It is a continuous sequence of adjustments in which gravity, pressure, temperature, and chemical composition are always interacting to create a new state. When the hydrogen in the core is no longer sufficient to sustain fusion in the old way, the star enters a different phase. Exactly what happens next depends greatly on its mass. A star with a mass similar to the Sun may allow its core to contract while its outer layers expand, becoming larger and cooler at the surface. A more massive star may reach temperatures high enough to ignite further kinds of nuclear reactions, creating heavier elements through a complex sequence of stages. Smaller stars may follow a gentler and slower path, never passing through all the phases that larger stars are capable of reaching. Although their paths may differ, all stars share the need to continually adapt to the changing fuel within them. When one kind of reaction weakens, the structure contracts. When that contraction raises the temperature enough, a new reaction may begin. When more energy is produced, the outer layers may expand. The life of a star is therefore a long rhythm of contraction and expansion, of accumulation and release, of gravity, always drawing matter deeper inward, while thermal energy continually seeks a way to escape. None of these stages occur because the star actively chooses them. There is no control center and no predetermined plan. Every change is simply the result of physical laws acting upon an immense body of matter over an extraordinarily long time. It is the simplicity of these basic laws, repeated on such a vast scale, that creates the many different lives of stars and shapes so beautiful that humanity has needed centuries to begin understanding them. For most of human history, stars were seen only as distant points of light, useful for navigation or for marking positions on maps of the sky. We cannot touch them, collect samples from their cores, or directly follow a single star from birth to death, because a human lifetime is far too short compared with the timescale of a star. And yet the light that stars send across space carries an extraordinary amount of information. When starlight is separated into a spectrum, it appears as a band of color marked by distinctive dark and bright lines. Each element absorbs or emits light at its own particular wavelengths, so these lines act almost like fingerprints of matter. From a spectrum, astronomers can determine which elements are present in a star's atmosphere, how hot its surface is, how quickly it is rotating, and whether it is moving toward us or away from us. Brightness and color also allow scientists to compare many different stars, place them into groups with similar characteristics, and recognize that they are not unchanging objects. By observing millions of stars of different ages, masses, and environments, we can piece together a picture of stellar evolution. It is much like looking at a forest filled with young trees, mature trees, and ancient trees in order to understand how a single tree changes over time. Even though no one can stand beside one trunk for thousands of years and watch its entire life unfold. Star clusters are especially useful in this process because the stars within a single cluster usually formed at nearly the same time and from the same cloud of gas. By observing them, astronomers can see that the most massive stars have already moved farther along in their evolution, while the smaller stars remain in their stable phase. From this difference, an important rule gradually becomes clear. Mass determines not only how hot or bright a star will be, but also has a profound influence on the entire pace of its life. Before going deeper into that principle, there is a very natural misunderstanding that needs to be cleared up. When we hear that a star uses fuel, it is easy to imagine something like a pile of wood burning or a container slowly being emptied. But the reactions inside a star do not work in such a simple way. The fuel is not fed into a single flame, and the light does not escape immediately after each reaction. The entire star is an interconnected system where temperature, density, chemical composition, and the movement of matter all help determine the rate at which energy is produced. If the core becomes slightly hotter, the reaction rate may increase, producing more energy and causing the interior to expand a little, which then lowers the temperature. If less energy is produced, gravity may cause the core to contract, raising the temperature and making the reaction stronger again. This self-regulating mechanism allows a star to remain stable across extraordinarily long stretches of time. It is like a system that continually finds its way back toward equilibrium, not perfectly, but reliably enough for a star to shine longer than the entire history of a living species. Yet self-regulation cannot create new fuel from nothing. Every reaction changes the composition of the core, and those changes accumulate over time. A star may extend its life by using fuel more slowly, mixing its material more efficiently, or adjusting its internal structure, but it cannot completely avoid the eventual decline of the energy source it depends on. In that sense, the light of a star is always borrowed from a limited state of matter. Over millions or billions of years, the transformation happens so slowly that the star may appear unchanging, yet every moment it shines carries it one step farther through its life. There is no need to think of this only as a loss. It is precisely because matter changes that energy can be released, light can travel across space, and nearby planets can receive warmth. If hydrogen did not transform, stars would not shine. If gravity did not draw matter together, clouds of gas would never become hot enough for fusion to begin. If energy could not find its way outward, the night sky would hold no points of light, and Earth would receive none of the energy that allows life to exist. Light and change, then, are not opposites. They are two parts of the same process. When we look at a star, we are seeing matter in a temporary state, though one that can endure for an immense span of time. Before this, that matter may have rested within a cold cloud. Later, it may become a small remnant, an expanding cloud of gas, or part of another generation of stars. Between those states lies the long interval in which the star shines, maintains an almost stable form, and sends energy outward into space. That interval may last long enough for planets to form, cool, transform their surfaces, and perhaps develop complexities the star itself will never know. But no matter how long it lasts, this phase still depends on one very specific question. How quickly is the star using its energy? A star containing more matter may seem to possess a larger store of fuel, but greater mass also means stronger gravity, a hotter core, and faster reactions. A smaller star has less fuel, yet the gentler conditions within its core may allow it to consume that fuel far more slowly. This is where our familiar intuition begins to fail, because the greatest source of light is not necessarily the one that lasts the longest. The sky today contains stars shining with an intensity almost beyond imagination, alongside others that emit only a tiny fraction of the sun's light. All of them are governed by the same basic principles, yet the rhythms of their lives are profoundly different. Some stars pass through most of their lives in a period that, on a cosmic scale, is shorter than the lifespan of certain species on Earth. Others may continue shining for so long that the present age of the universe would seem like only the briefest opening chapter. To understand why this difference is so enormous, we need to look at a principle that may seem paradoxical, yet lies within the structure of every star. As mass increases, the amount of fuel also increases, but the rate at which that fuel is consumed rises much faster. And for that reason, the brightest stars in the sky are often not the ones that remain the longest. The brightest stars in the sky are often not the ones that remain the longest. At first, this may seem counterintuitive, because a massive star contains more matter, which also means it possesses a larger supply of fuel. If we consider only the amount of hydrogen it carries from the time of its formation, we might expect a giant star to shine longer than a smaller one. In reality, the opposite is true, because a star's lifetime depends not only on how much fuel is available, but also, and very deeply, on how quickly the star is compelled to use it. Imagine a vast, star-forming region where thousands of stars are born from the same cloud of gas. Their origins are much the same, and they appear within roughly the same period of time, yet their masses are not all identical. At one end are small stars containing only a fraction of the sun's mass. Near the middle are stars similar in size to the Sunday. At the other end are a small number of giants, with 10, 20, or even more times the mass of the Sunday. During the first few million years, the largest stars are usually the easiest objects to notice. They shine intensely, have extremely hot surfaces, and appear blue or blue-white. Their radiation floods the surrounding clouds of gas, causing the material to glow in soft, luminous outlines. Seen through a telescope, the eye is almost naturally drawn toward these massive stars because they outshine nearly everything around them. The smaller stars are present within the same scene, but most are lost in the brilliance of the giants. They do not create vast glowing halos, they do not dominate the surrounding clouds, and they rarely become the most striking features in an astronomical image. Their presence is quieter, like tiny points of light beneath a sky overwhelmed by brighter sources. If we return to that same star-forming region, several million years later, the scene would already be changing. Some of the most massive stars would have left their stable phase. They would have swollen, altered their internal structures, and become increasingly unstable. A few might already have ended their lives in powerful explosions, leaving behind neutron stars or black holes. The stars that once shone the brightest would also be the first to disappear from the scene. Meanwhile, the smaller stars would continue almost as they had before. Their brightness would have changed very little. Their forms would remain stable. Much of the hydrogen in their cores would still be unused. They would endure through the transformation of the space around them, continuing to shine long after their more brilliant neighbors had become remnants. The reason for this difference lies deep within the core, where mass determines the strength of gravity. The more massive a star is, the more strongly the weight of its outer layers presses down upon its center. The core is compressed more tightly, its density rises, and its temperature increases. In that environment, atomic nuclei move faster and collide more frequently, allowing nuclear fusion to proceed at a much greater rate. Mass, then, does not simply give a star more fuel. It also makes the machinery inside the star operate far more intensely. A star with twice the mass of the Sun is not merely twice as bright. In many cases, its luminosity may be several times greater than that. As mass continues to increase, the difference becomes even more dramatic. A massive star may contain tens of times more hydrogen than the Sun, yet release energy thousands or even tens of thousands of times more powerfully. Its larger fuel supply cannot compensate for the extraordinary rate at which that fuel is consumed, and so the star's life is shortened considerably. We might imagine two people preparing for a long journey. The first carries a small bottle of water, but drinks only a few slow sips at a time. The second carries an entire tank, yet uses hundreds of times more water every minute. The larger supply may seem abundant, but if the rate of use increases faster than the reserve itself, the person carrying more can still run out first. Massive stars live under similar conditions. Their powerful gravity does not allow them to shine modestly. To prevent their enormous mass from collapsing inward, their cores must produce tremendous amounts of energy. That energy creates enough pressure to support the layers of matter above. A massive star cannot simply slow its reactions to the gentle pace of a smaller star, because if too little energy were produced, gravity would compress the core, the temperature would rise, and fusion would become more intense once again. A star's structure adjusts itself into a state suited to the mass it carries. In a small star, equilibrium can be maintained at a relatively low core temperature. In a massive star, equilibrium requires a hotter core, greater pressure, and a much higher rate of energy release. It is this need to support their own immense mass that causes giant stars to consume their fuel so quickly. In stars with masses similar to the Sun, hydrogen is converted into helium mainly through a sequence of reactions known as the proton-proton chain. This process proceeds steadily under the conditions found in the cores of medium-sized stars. As mass increases and the core grows hotter, another mechanism begins to play a more prominent role. Carbon, nitrogen, and oxygen can act as intermediaries, allowing hydrogen to be converted into helium through the CNO cycle. This cycle is especially sensitive to temperature. Even a relatively small increase in core temperature can cause the rate of energy production to rise sharply. So inside a massive star, higher temperatures do not merely make the reactions slightly faster. They can dramatically increase the rate at which energy is released. The star becomes brighter and hotter, while also passing through its hydrogen supply far more rapidly. The blue light of massive stars is a sign of their extremely high surface temperatures. In everyday life, blue often gives the impression of coldness, but in astronomy, blue stars are the hottest stars of all. Their surfaces can be several times hotter than the surface of the Sunday. Their cores are even more extreme, filled with matter in the form of plasma, where atoms have lost their electrons and charged particles move through an environment heated to tens of millions of degrees. From a great distance, all of this violence appears only as a quiet point of light. No sound can travel through the vacuum to tell us how intensely the matter inside is moving. There are no flickering flames like those we see on Earth. There is only a continuous flow of light, so steady that the star seems calm even while it is consuming fuel at an immense rate. The stillness on the outside can sometimes conceal a very rapid life within. A star with a mass similar to the Sun can remain in its stable hydrogen burning phase for about 10 billion years. The Sun has already passed through nearly half of that span. Smaller stars may live far longer because their cooler cores allow reactions to proceed more slowly. By contrast, a star with roughly 10 times the Sun's mass may remain stable for only a few tens of millions of years. Even more massive stars may pass through most of their lives in only a few million years. A few million years is an immense span when viewed from the scale of human life. Mountain ranges can erode, climates can change, and countless species can appear and vanish. On the cosmic time scale, however, a few million years is remarkably brief. Some giant stars are born, live out their entire lives, and disappear, while a smaller neighboring star has barely changed at all. If the lifetime of a massive star were placed on a clock representing the life of the Sun, it might survive for only the first few minutes. Its light would be far more powerful, but its time to shine would be much shorter. The smaller star would never produce the same brilliant display, yet it would remain long after most of the clock had passed. This helps explain why young star-forming regions often contain many bright blue stars, while older stellar populations do not. The blue stars do not disappear because the color of an entire galaxy changes with age. They disappear first because their lifetimes are so short. After enough time has passed, only the smaller stars remain, causing the combined light of the population to gradually shift toward warmer colors. Astronomers can observe this pattern in star clusters. A cluster is like a large family whose members were mostly born at nearly the same time from the same cloud of gas. Because their ages are relatively similar, the differences in their evolution arise mainly from the masses they possessed at birth. In a young star cluster, massive stars may still be present in their stable phase. On a diagram showing luminosity and temperature, they appear in the bright, hot region. In an older cluster, the largest stars have already moved away from that position. Some have entered their giant phases, while others have completed their lives. Only the lower mass stars continue to sustain stable hydrogen fusion. The point where stars begin to leave this stable phase is known as the main sequence turnoff. Its position allows scientists to estimate the age of the entire cluster. If only the most massive stars have moved away, the cluster is still young. If stars with masses similar to the Sun are also beginning to change, then the cluster has existed for much longer. Through this kind of observation, we do not need to follow a single star for billions of years. We can look at many clusters of different ages, like opening a book to several pages and then arranging them in the correct order. Each cluster provides one part of the story, from regions still filled with young blue stars to older populations dominated by smaller ones. The picture that emerges is quite clear. Greater brightness usually comes with a faster pace of life. Massive stars do more than consume hydrogen more quickly. Once the hydrogen in their cores begins to decline, they can also move through several additional stages of nuclear fusion. The core contracts, the temperature rises, and helium begins to form heavier elements. In stars massive enough to continue, the process moves through a series of layered reactions, producing carbon, oxygen, neon, silicon, and eventually elements close to iron. Each new stage is usually shorter than the one before it. Hydrogen may be used for millions of years. Helium is consumed over a shorter period. The final stages can unfold so rapidly that the star's entire internal structure changes dramatically within a span that is tiny compared with the life it has already lived. A massive star, therefore, lives through a sequence of increasingly rapid rhythms. Its first stage is already shorter than that of a small star, and the later stages become shorter still. As it moves deeper into its life, the star must reach ever higher temperatures to sustain new reactions, while the amount of energy available from each step becomes increasingly limited. Eventually, the old balance can no longer be maintained. The exact ending depends on mass, composition, rotation, and many other factors. Some stars cast their outer layers into space before their cores collapse. Some end in supernova explosions. Others may collapse so completely that they form black holes without producing the kind of bright display we usually imagine. These endings vary greatly, but they all begin with the same underlying cause. A large mass sets a rapid pace for the star from the very beginning. Brilliant light does not come without a cost. It is the visible expression of an intense rate of energy conversion, a process that is continuously transforming the matter within. While a giant star passes through all of these stages, a smaller star may still be quietly converting hydrogen into helium at an almost unchanged pace. Because it does not need to produce enough pressure to support an enormous mass, its core operates under gentler conditions. The slower reaction rate allows its fuel to last. Its dimmer light means that with every passing second, the star uses only a small portion of its reserves. This difference is not quite the same as one object choosing to be careful while another chooses to be wasteful. A star cannot decide to live more slowly. Its pace is determined by its mass from the moment it forms. Mass determines the strength of gravity. Gravity shapes the temperature of the core, and the core temperature controls the rate of fusion. From one initial property, the entire life of the star gradually unfolds according to the laws of nature. There is a simple beauty in this chain of connections. By knowing how much a star weighs, scientists can estimate many things about it: its surface temperature, luminosity, color, the way it transports energy, how long it will remain stable, and even the kind of remnant it may leave behind. Not every detail can be predicted perfectly, but mass remains the most important factor shaping the life of a star. If we could travel through the galaxy today, we would encounter stars living at many different rhythms. A giant blue star might release energy so powerfully that its radiation drives gas away from its surface, creating stellar winds that extend across trillions of kilometers. Nearby, a smaller star might shine so faintly that it barely affects the surrounding environment. The blue star draws every eye, while the smaller star is almost unnoticed. After a few million years, the blue star has changed completely. The small star is still there. After hundreds of millions of years, the surrounding clouds of gas may have dispersed, the cluster may have begun to break apart, and its members may have drifted into different orbits around the galaxy. The small star continues to exist. Even after billions of years, it may still be somewhere near the middle of its stable life. When enough time and if brilliance cease, the advantage of brilliance begins to disappear. The massive stars are no longer there to overwhelm the fainter sources of light. The small stars that once remained in the background become the longest-lasting objects in the scene. They have not won a competition, because the universe is not holding a race. They are simply built in a way that allows each second of light to consume less fuel. This brings us closer to the image of the final star. If the last remaining source of starlight must survive for trillions of years, it cannot continue releasing energy with the intensity of a giant star. Such a source must be smaller, cooler, and slower. It must maintain just enough temperature in its core for hydrogen fusion to continue, but not so much that its fuel is consumed too quickly. Between a giant star and a small one, the difference is not only a matter of visible size. They represent two different ways for time to move through matter. For a massive star, a few million years may be enough to complete an entire life. For a small star, that same span may amount to only the faintest change, almost impossible to detect even with the most precise instruments. On Earth, prominence often makes something seem more important. A tall mountain catches the eye more easily than a small stone. A flash of lightning brightens the sky more dramatically than moonlight. In the universe, brightness also makes giant stars easier to remember. They create heavy elements, reshape the space between stars, and may end their lives in spectacular events. But when the question is no longer which star shines brightest, and instead becomes which star lasts the longest, our attention must shift toward more modest sources of light. The stars that do not dominate the sky may be the ones that carry their light farthest into the future. Even the sun, a star with an extraordinarily long lifetime by every human standard, is not a candidate for the final source of starlight. The sun is too massive to conserve its fuel in the most efficient way. It will continue shining steadily for billions of years, then its internal structure will change, its outer layers will expand, and its core will eventually become a white dwarf. It is a long life, but still far shorter than the lifetimes possible for the smallest stars. Below the sun, on the scale of stellar mass, lies an enormous population of faint stars, so common that they may make up most of the stars in the galaxy. Their surfaces are cooler, their light carries a deeper red color, and their rate of energy production is low. For much of the history of astronomy, many of these stars remained invisible to the naked eye, even though some are closer to us than many famous bright stars. It is within this overlooked population that the answer begins to appear. To outlast every giant star, a star must do more than burn its fuel slowly. It must also use the fuel inside it more efficiently, carrying hydrogen from different regions into the places where fusion can occur. The smallest stars possess a special internal structure that allows them to do this in a way the sun cannot. When we look at a faint red point among billions of stars, we may be seeing a source of light that has completed only a tiny fraction of its life. Larger stars born at the same time may have vanished long ago, while that red point continues to endure, moving more slowly than any clock humanity has ever built. In the least noticed corners of the galaxy, the answer gradually comes into view: red dwarfs, small and quiet, yet capable of surviving longer than any other source of starlight. In the least noticed corners of the galaxy, the answer gradually comes into view: red dwarfs, small and quiet, yet capable of surviving longer than any other source of starlight. If we look at the sky with the unaided eye, we barely notice most stars of this kind. They do not shine as brightly as Sirius, do not stand out within familiar constellations, and do not possess the brilliance of the blue stars often seen in astronomical images. Most red dwarfs emit only a small amount of light, often hundreds or thousands of times less than the sunday. As a result, even when they are very close to us, they can remain completely hidden from view. The nearest star to the solar system offers a beautiful example of this quiet presence. Proxima Centauri is just over 4 light-years away, a very small distance compared with the width of the Milky Way, yet it is too faint to be seen with the naked eye. Many stars that are tens, or evil, of Father and Ka, Hamis, I many star, now many, sometimes, nam times, amen, tu, hein may, highness, heinst. The objects right beside us require patience and the most delicate instruments before they can be seen. Although faint, red dwarfs are far from rare. They may make up most of the stars in the Milky Way, appearing throughout the galactic disk, within old star clusters, across the sun's local neighborhood, and in regions of space unconnected to any famous constellation. If we could travel through the galaxy and count every star, we would encounter red dwarfs far more often than stars like the Sunday. This is somewhat different from the impression created by the night sky. Bright stars easily attract our attention, leading us to imagine that they represent the most common form of a star. In reality, the sun belongs to a group that is larger and brighter than most stars in the galaxy. Red dwarfs, though much harder to see, are the small lamps the universe produces in the greatest numbers. Their name can sometimes create a slightly misleading image. The phrase red dwarf may suggest an old star that is cooling down and holding on to only the last traces of its light. But these are not stellar remnants. They are still active stars, still sustaining nuclear fusion in their cores and still converting hydrogen into helium, just as the sun is doing now. The word dwarf simply means that they are smaller than the sun, while their red color comes from their lower surface temperatures. If the sun appears nearly white with a yellowish tint when seen from Earth, red dwarfs usually glow with softer shades of orange or red. They are not vivid red like a burning coal, but more like a warm, gentle, and very modest source of light. The smallest red dwarfs lie close to the boundary between a true star and an object without enough mass to sustain hydrogen fusion. If such an object were only slightly lighter, it would become a brown dwarf, remaining warm for a time but unable to maintain the same kind of nuclear reaction across trillions of years. If it were just slightly heavier than that threshold, gravity would compress its core strongly enough, the temperature would rise just high enough, and a tiny star could begin a life so long that the present age of the universe would seem almost brief beside it. What makes these stars special is not only that they use their fuel slowly, their internal structure also allows a very large portion of their hydrogen to be carried into regions where it can take part in fusion. To understand this difference more clearly, we can imagine the interior of the sun divided into regions that transport energy in different ways. At the center is the core, where nuclear fusion occurs. Surrounding the core is a broad region where energy moves mainly through radiation. Farther out lies the convective zone, where hot matter rises, cools near the surface, and then sinks again. This division helps the Sun maintain a stable state, but it also prevents hydrogen in the outer layers from being easily carried all the way down into the core. The Sun contains a great deal of hydrogen throughout its entire mass, yet during its present stage, only the matter within the central region is directly used in its main fusion reactions. In low-mass red dwarfs, the boundaries between internal regions are not defined in quite the same way. Convective motion can extend through nearly the entire star. Hot material from deep inside slowly rises, while cooler material from above sinks downward. Hydrogen is carried toward the center, while the helium produced in the core is distributed into other regions. This process continues constantly and very slowly, like a deep ocean mixing itself through vast currents that the human eye could never detect in a single moment. There is no surface of water, no wave, and no sound, only hot plasma circulating within a small sphere held together by gravity. This image helps us understand why red dwarfs can use their fuel so efficiently. The Sun is like a large house with many reserves, but not every room is easy to reach. A smaller red dwarf is more like a space in which every region is continuously exchanging material, allowing hydrogen far from the center to be carried gradually into the fusion zone. It does not possess more fuel than the Sunday. In fact, it contains far less matter, but almost all of that reserve can eventually be used, while the rate of consumption remains extraordinarily slow. This is the combination that gives red dwarfs their remarkable lifetimes: less fuel, but used more steadily, more slowly, and far more completely. Inside a massive star, high temperatures cause fusion to proceed rapidly. Inside a red dwarf, the core temperature is only just high enough to sustain the conversion of hydrogen into helium. The reactions continue, but there is no urgency. Each second, the star produces less energy, less light escapes into space, and its fuel supply can therefore endure across spans of time that are almost impossible to imagine. While the Sun can remain in its stable phase for about 10 billion years, many red dwarfs may survive for hundreds of billions of years. The smallest stars, lying just above the threshold required to become a star, may continue shining for trillions of years. These numbers are so large that repeating them does little to help the mind truly grasp them. Perhaps it is easier to imagine compressing the entire life of a red dwarf into a single year. On that imaginary calendar, the universe today would have passed through only the first few days of January. Everything that has happened since the earliest galaxies formed, including the birth of the Sun, Earth, and the whole of human history, would occupy only a tiny fraction near the beginning of the year. Almost the entire spring, summer, autumn, and winter would still lie ahead, untouched by the star. The universe is currently about 13.8 billion years old. To a human being, that is a span of time that feels almost infinite. To the smallest red dwarf, it may represent only the brief opening of a life lasting trillions of years. This leads to a remarkably peaceful truth. No small red dwarf in the universe today has ever truly grown old. Even red dwarfs born when galaxies were still young have used only a small portion of their hydrogen. No star belonging to this longest-lived group has completed its stable phase. No telescope has ever observed a small red dwarf reaching the natural end of its entire life, because the universe has not existed long enough for that to happen. We can see young giant stars, sun-like stars in the middle of their lives, red giants that have entered their later stages, and remnants left behind after many kinds of stars have completed their evolution. But for the smallest red dwarfs, nature has shown us only the beginning. We might imagine humanity holding a very long book, while every red dwarf we can observe is still somewhere within its opening chapters. The later pages have never appeared in reality. They can only be constructed from what we understand about gravity, nuclear fusion, the movement of matter, and the balance within stars. Scientists understand the future of red dwarfs not by waiting trillions of years, but by observing many different stars, measuring their masses, temperatures, luminosities, and compositions, and then using well-tested laws of physics to calculate how they will change from one stage to the next. The light of a star carries far more information than its appearance alone might suggest. When separated into a spectrum, that light reveals the star's surface temperature, the elements present in its atmosphere, and even its motion through space. If a red dwarf belongs to a binary system, the movement of the two stars around each other also allows astronomers to measure their masses with considerable precision. Those measurements are then entered into computer models. A model begins with a star of a particular mass and composition, then calculates how hot its core becomes, how quickly its reactions proceed, how energy is transported outward, and how its chemical composition changes. After each small step, the newly calculated state becomes the starting point for the next. Through countless steps like these, scientists can follow a star within the imagined passage of physical time, carrying it across billions and then trillions of years without waiting for that time to pass in reality. There are still uncertainties in this distant future. No model can turn a span of trillions of years into an absolutely precise prediction. Chemical composition, magnetic fields, and interactions with other objects can all create differences. Even so, the central principle is clear. Small red dwarfs have relatively cool cores, slow reactions, and deep internal mixing, giving them the ability to survive far longer than larger stars. For most of their lives, their changes are so subtle that they are almost impossible to notice. If we observed a red dwarf for 1,000 years, its average brightness would appear nearly unchanged. Even 1,000,000 years would still be only a brief interval. These stars do not live according to the rhythm of centuries or millennia. Their pace is measured in billions of years. This does not mean that red dwarfs are always completely calm. Some possess powerful magnetic fields that create star spots and flares capable of increasing their brightness for short periods. Young stars that rotate rapidly are often more active, while as they age, their rotation tends to slow and their flares may become less frequent. Seen up close, a young red dwarf may not appear gentle at all. Its surface can shift, its magnetic fields can twist, and then stored energy can suddenly be released. But these disturbances occupy only a tiny fraction of the star's entire existence. Over billions of years, it gradually spins more slowly, its activity settles, and it continues along its long path at a steadier pace. There is an interesting contrast here. A red dwarf may produce powerful flares over short periods, yet its entire life is one of the slowest processes in the universe. A few minutes of surface activity do not change the fact that the fuel in its core is still being consumed at an extremely low rate. As hydrogen is gradually converted into helium, a red dwarf does not preserve its original appearance forever. Changes in its internal composition cause the star to slowly adjust its structure. Over time, its core may become slightly hotter, its luminosity may increase, and its color may gradually shift. Contrary to what we might expect, an aging star does not necessarily continue to grow dimmer. For a red dwarf, the later part of its life may be brighter than the beginning. As helium accumulates, the material within becomes denser. The star contracts slightly, and its temperature rises, allowing energy to be produced more rapidly than during its earliest stages. Even this transformation unfolds with extraordinary slowness. There is no single distinct moment when a red dwarf suddenly becomes brighter. Across billions of years, the difference increases only a little at a time, like the light of dawn slowly spreading, until no one can identify the exact moment when night came to an end. The lightest red dwarfs may never develop into red giants like the sunday. In the future, the sun will expand until its outer layers become immense. A small red dwarf, however, is deeply mixed, so its aging process may follow a different path. Instead of swelling into a giant sphere, it may gradually become hotter, brighter, and shift toward a paler color. Models refer to this future stage as a blue dwarf. The name does not mean that the star will become a deep blue like a gemstone. It simply means that its light will gradually shift toward shorter wavelengths compared with its original red glow. No blue dwarf exists in the universe today, at least not one that has reached that state through natural stellar evolution. They belong to a very distant era, when the earliest red dwarfs have passed through most of their immensely long lives. Like the old age of red dwarfs themselves, blue dwarfs currently exist only within models, as images of a future the universe is still far too young to have reached. This makes red dwarfs a particularly unusual kind of star. They are the most common, yet the final stages of their lives have never been observed. They are close to us, yet most cannot be seen with the naked eye. They contain less matter than the sun, yet they may preserve their light for hundreds or thousands of times longer. If a small red dwarf had formed at that same time, Mesa's sun, Phazon, it would still be fusing hydrogen long after the sun had completed its life and become a slowly cooling remnant. When the constellations we know today had changed beyond recognition, it would still be shining. When most sun-like stars had already left their stable phase, it would still hold a vast reserve of fuel. As time passes, the brilliant stars disappear from the scene first, while smaller sources of light gradually become more noticeable. This is not because red dwarfs become powerful in the familiar sense, but because the stars that once outshone them are no longer there. An aging galaxy may no longer contain giant blue stars illuminating clouds of gas, yet it could still hold countless red dwarfs. Its overall light would be gentler, warmer in color, and slower to change. If an observer existed in that distant era, their sky might not be as brilliant as the skies surrounding young star-forming regions, but it would not yet be completely dark. Small red points would continue to remain, preserving the age of starlight far longer than any massive star. Among them, the smallest stars would last the longest. They lie just above the threshold required to sustain nuclear fusion, producing only enough energy to prevent further contraction, but not so much that their fuel is consumed quickly. They can be thought of as the slowest clocks nature has ever created, with each change requiring spans of time longer than the present ages of many galaxies. It is here that the image of the final star begins to become clearer. It may not be a massive object at the center of a galaxy, nor a star that attracted attention during its youth. More likely, it will belong to the small, cool, and difficult-to-see population, a source of light that has lived quietly through countless ages, while everything around it slowly changed. But a long lifetime alone is not enough to determine which star will remain until the very end. The time when a star is born also matters greatly. A red dwarf that forms later may continue shining after an ancient red dwarf has faded, even if the two stars have nearly identical lifetimes. At this moment, the Milky Way is still creating new stars. Clouds of gas are still collapsing, protostars are still growing, and new sources of light are still appearing within dark regions of dust. This process will not end in the near future. It may continue across immense spans of time, gradually slowing as the supply of gas within galaxies changes. So, to find the final star, we need to know more than which kind of star lives the longest. We also need to understand how long the universe can continue creating new stars. A red dwarf may scarcely know what it means to grow old, but the final surviving source of starlight will likely be a red dwarf born during a much later era, when galaxies have become quieter and the appearance of each new star has grown rarer than before. From here, our journey will leave the deep interior of a small star and widen to include the entire galaxy, where clouds of gas are slowly changing, star-forming regions are gradually consuming their material, and new generations of light continue to emerge. Because before we can imagine the final star still shining, we must first understand when the universe will create one of the last stars ever to be born. Before we can imagine the final star still shining, we first need to understand when the universe will create one of the last stars ever to be born. To begin, let us move away from the small red dwarf that appeared in the previous chapter and draw back a little farther, until the entire star becomes nothing more than a point of light within the galaxy. From that distance, we can see dark lanes of dust Stretching along the spiral arms, faint clouds of gas illuminated by young stars, and countless regions that seem empty but still contain atoms drifting slowly through space. Every star that has ever appeared in this scene began with matter lying between the stars. So the story of how light is born is also the story of the long journey of gas through a galaxy. We can follow that journey through an imaginary hydrogen atom. It does not need a name, because the universe contains so many atoms like it that their number lies far beyond any familiar way of counting. For a time, this atom may drift through a region of hot, thin gas, many light years from the nearest stars. It moves with the galaxy, passing through areas of different density and responding to gravity, magnetic fields, and slow waves traveling through the interstellar medium. Most of the time, nothing remarkable happens. The atom simply continues to drift, like a tiny grain of dust carried along by a vast current whose full shape it could never see. As it enters a cooler region of gas, its motion slows slightly. More atoms begin to gather around it. The distances between them gradually decrease, and over time, a cold cloud of gas begins to form. Clouds like these do not always create stars. They may drift through a galaxy for millions of years, stretched by its rotation, compressed as they pass through a spiral arm, or stirred by nearby stars. Only when a region within the cloud becomes cold enough, dense enough, and massive enough does gravity begin to overcome the motions, keeping the gas dispersed. At first, the contraction happens very slowly. A small region of gas gradually gathers more matter. Its density rises, the temperature at its center changes, and the larger cloud begins to break apart into smaller regions. Each of these regions may continue collapsing into a protostar, while around some of them, the remaining material forms broad disks where planets may eventually take shape. Our imaginary hydrogen atom may fall into one of these regions. After drifting between the stars for an immense span of time, it becomes part of a new star. If that star is small enough, the atom may remain as hydrogen for a very long time before reaching the core. If it is carried into a region where the temperature and pressure are suitable, it will take part in the chain of reactions that produces helium, while a tiny fraction of its mass is converted into energy and slowly travels outward as light. It is a beautiful cycle of matter. Interstellar gas gathers into a star. The star uses part of that matter to produce energy, and during its later stages, some of the material may return to space. Stars like the Sun release their outer layers as they age. Massive stars produce powerful stellar winds, and some end in explosions that send matter across great distances. Elements once held in stellar cores or deep internal layers are scattered throughout the galaxy, mixing with the hydrogen and helium already present. In this way, some matter may become part of several generations of stars. It may once have existed inside an older star, returned to space, entered a new cloud, and then become part of another star. The carbon atoms in the human body, the oxygen in the air, and many of the elements found in rocks and soil were created or transformed inside stars before they ever became part of Earth. A galaxy, then, is not simply a collection of separate points of light. It is more like a vast ecosystem of matter, where gas passes through different stages. One generation of stars influences the next, and new light is created from what older stars have left behind. But this cycle is not completely closed. Each time a new generation of stars forms, some of the gas becomes locked inside stars that live for extremely long periods. Another portion becomes white dwarfs, neutron stars, black holes, planets, or smaller objects that do not easily return their matter to the surrounding environment. Some gas is heated so intensely that it cannot collapse again quickly. Other material is pushed into the vast halo surrounding the galaxy, where the density is too low for stars to form in the usual way. This does not mean that a galaxy suddenly loses its ability to create stars. The change happens much more slowly. We might imagine a large lake fed by many streams, while water is also continually leaving in different directions. If the flow entering the lake gradually decreases, While water continues to be retained or carried away, the level will fall very slowly. Over a short period, the landscape may appear almost unchanged. Only after many seasons does the difference become clear. The reservoir of cold gas within a galaxy can be imagined in much the same way. During earlier eras, many galaxies received large amounts of gas from their surroundings. Streams of matter followed the cosmic web, fell into regions of strong gravity, and supplied material to star-forming clouds. Smaller galaxies could also merge, bringing in fresh gas and disturbing the material already present, creating periods of more intense star formation. When the universe was young, it formed stars at a faster rate than it does today. Many galaxies contained abundant gas and frequently experienced collisions and mergers, compressing clouds and producing new generations of stars. Looking across very great distances also means looking into the past, and within that ancient light, astronomers observe many galaxies glowing intensely because stars were forming within them at a rapid pace. From that era to the present, the average rate of star formation across the universe has declined. The Milky Way is still producing new stars, and regions such as the Orion Nebula still contain many growing protostars. But the galaxy as a whole is no longer as active as it was during certain periods in the distant past. This process is not like a door closing in a series of clearly defined steps. It is more like an immensely long piece of music gradually slowing down, with longer pauses appearing between the notes while the melody continues. Within each galaxy, many factors determine whether gas can form stars. First, the gas must cool. When matter is too hot, its particles move rapidly and have difficulty gathering into dense regions. If the gas can release some of its energy as radiation, its motion slows, allowing gravity to draw it together more easily. The gas must also reach a suitable density. A large amount of matter spread across too wide an area will not form a star. Only when it gathers into clouds dense enough can smaller regions within them collapse under their own gravity. Interstellar dust also helps the gas cool and shields fragile molecules from intense radiation, creating an environment more favorable for star formation. The rotation of a galaxy, magnetic fields, and turbulent motion within clouds can all slow or guide the process of collapse. A cloud does not simply fall straight toward its own center. It vibrates, rotates, breaks apart into many regions, and exchanges energy with its surroundings. It is this complexity that allows a star-forming region to produce many stars of different masses instead of forming a single luminous object. Once young stars appear, they begin to influence the gas around them. Ultraviolet light from massive stars ionizes and heats the gas. Stellar winds carve broad cavities through the cloud. Explosions from massive stars can compress certain regions and create conditions that allow new stars to form, while also pushing other gas away and interrupting the process already underway. A generation of stars can therefore help begin the next generation, while also making the environment less favorable for further star formation. Which effect becomes stronger depends on the mass, density, location, and history of each region. A galaxy does not operate like a machine with a simple on and off switch. It is a constantly self-adjusting system in which matter moves between many states, and every change gives rise to others. At the centers of many galaxies lie supermassive black holes. When matter falls toward them, the surrounding region can release enormous amounts of energy. Outflows and radiation from the galactic center can sometimes heat gas across vast areas, making it difficult for that gas to cool and form stars. In large galaxies, this mechanism may help reduce star formation over time. Even so, not every galaxy ages in the same way. Some consume their gas quickly, forming many stars over a relatively short period before becoming quiet. Some smaller galaxies maintain a low rate of star formation for a very long time. Others may remain inactive for a while, only to form a new generation of stars after an interaction or an influx of fresh gas. This diversity means that the future of starlight cannot be described by a single date. There will be no moment when every galaxy stops creating stars at once. In one region, star formation may have almost completely ended, while another still contains cold clouds. One galaxy may already have become red and quiet, while a smaller galaxy elsewhere continues producing new stars at a slow pace. If we could observe the universe across tens of billions of years, we would see the overall colors of many galaxies gradually change. Massive blue stars always have short lifetimes, so they appear only where new stars are still being formed. As that activity declines, the blue light fades first. Smaller, longer-lived stars continue to shine, giving the galaxy a warmer color. Spiral arms, once highlighted by glowing regions of gas, would become softer and dimmer. Giant molecular clouds would appear less often. The intervals between new generations of stars would grow longer, as though the galaxy were spending more and more of its time at rest. This would not be complete silence. Existing stars would continue moving along their orbits. Planetary systems would still circle their stars. Red dwarfs would continue consuming hydrogen at an extremely slow pace. Stellar remnants would interact through gravity, while thin gas continued drifting through vast regions of space. Only the dawns of new stars would become rarer. In the very distant future, much of the gas may have become locked inside long-lived objects or stellar remnants. What remains may be too hot, too thinly spread, or moving along orbits that make it difficult to gather into dense clouds. By then, creating a new star in the familiar way would be far more difficult than it is today. But more difficult does not yet mean impossible. Even a very old galaxy may still contain small pockets of gas, cold clouds surviving in quiet regions, or material released by aging stars. Two streams of gas might meet and become compressed. A gravitational interaction could carry matter into a new region. Rare events like these might produce a few stars long after the great age of star formation had faded into the past. We might imagine a forest near the end of a season, when most seeds have already fallen and the winds carry fewer and fewer new ones. Growth is no longer as abundant as it once was, yet in one place where enough moisture remains, a seedling may still appear. It does not return the entire forest to spring, but its small presence reminds us that nature rarely moves from abundance to complete emptiness in a single step. In an aging galaxy, a star born so late could become something remarkable, not because it would be fundamentally different from stars that came before it, but because of the time in which it appeared. When most surviving stars had already grown very old, the birth of a young source of light would be like a new note sounding within a piece of music that had become sparse and slow. If that star were massive, it would still live quickly and disappear early. If its mass were similar to the sun's, its life might last billions of years, but not long enough to compete with red dwarfs. But if the remaining material formed a very small star, that new source of light could continue shining for trillions of years from the moment of its birth. This changes the way we search for the final star. The longest-lived star is not necessarily the last one still shining. A red dwarf formed very early may complete its life before a similar red dwarf born hundreds of billions or trillions of years later. The question, then, is not only which star possesses the slowest clock, but also when that clock begins to run. In even more distant ages, when ordinary gas clouds have almost completely stopped producing stars, a few rare pathways may still remain. One of them involves brown dwarfs, objects smaller than stars, and not massive enough to sustain stable hydrogen fusion. Today, there may be vast numbers of brown dwarfs moving through galaxies, most of them so faint that they are difficult to detect. Across immense spans of time, gravitational interactions can alter their orbits. Most will pass one another at great distances, but in a galaxy filled with many objects and given enough time, rare encounters can still occur. Two brown dwarfs might collide or merge. If their combined mass rises above the necessary threshold, the central region may become hot enough for hydrogen fusion to begin. From two objects that were never true stars, a new small star could emerge. This is a possibility predicted by theory for the far future, not an event we have observed under those conditions in the present era. The probability of any individual collision is extremely low, but the universe may provide something human life never can, an almost unimaginable amount of time. When time stretches far enough, an extraordinarily rare event is no longer entirely insignificant. A galaxy that has remained quiet for trillions of years might suddenly gain a small new source of light, not because a vast cloud collapsed as it did in the galaxy's youth, but because two dark objects finally met after an extraordinarily long journey. A star born in this way might be nothing more than a small red dwarf. It would not illuminate the entire galaxy, create a brilliant region of glowing gas, or signal the return of an abundant age of star formation. Its light would be enough only to form a warm point in the darkness, but because of its low mass, that point of light could continue to exist longer than almost every other remaining source. This image adds another layer to the story of the final star. Perhaps it will not be an ancient star that has endured since the early days of the universe. It may instead be young by the standards of its own era, born after galaxies have already lived through. New generations appear only within remaining pockets of gas or through less common circumstances. Eventually, new starlight becomes so infrequent that the intervals between its appearances may last longer than the entire present age of the universe. If we could observe a galaxy during that era, the scene might feel remarkably gentle. There would be few bright blue regions and no vast clouds glowing beneath the light of young stars. Most of the illumination would come from small, long-lived stars, spread across the galaxy as a faint halo of warmer light. Between them would drift countless remnants and dark objects, all still moving within the same gravitational field. The galaxy would not be asleep in any literal sense, because matter would never come to a complete stop. It would simply have entered a slower rhythm, one in which major events became increasingly rare and every change required more time before it could be clearly seen. At some point in the very distant future, a small cloud of gas might begin to collapse near the edge of a galaxy. No observer would be standing nearby, and there might be no crowded sky for the new light to join. Yet the process would still unfold according to familiar laws. The gas would grow denser, the temperature at its center would rise, a protostar would form, and hydrogen fusion would begin. The first light escaping from the surface of that star might enter a region of space that had not witnessed the birth of a new star for an unimaginably long time. It would not need to be bright. Simply by existing, it would mark another moment when matter had found its way back into a luminous state. That new star could continue its life, while the remaining gas in the galaxy became thinner and more widely dispersed. Other stars would complete their journeys, stellar remnants would cool, and the distances between active sources of light would grow. If the new star were a small red dwarf, its lifetime would begin at that late moment and continue for trillions of years beyond it. In this way, a galaxy does more than give the final star the right kind of body, a small, cool body that consumes its fuel slowly. It also determines when that star's clock begins to run. In the present day, this process is still unfolding around us. The Milky Way still contains abundant gas, and new stars continue to be born. Astronomers observe protostars hidden within dust using infrared light, follow streams of material flowing outward from young systems, and study disks where planets may slowly be taking shape. We live in a galaxy that has not yet entered a state of complete quiet. Part of the beauty of our present era lies in the way so many stages overlap. Within the same galaxy, there are clouds that have not yet formed stars, stars that have only just begun to shine, sun-like stars in stable phases, aging stars expanding outward, and remnants that have already passed through the main luminous chapters of their lives. The past, the present, and hints of the future all exist within a single picture. But when we look far enough ahead, that picture gradually becomes simpler. Star-forming regions grow rare, young stars appear less often, and red dwarfs provide most of the remaining light. Galaxies that once had clearly defined shapes may be transformed through interactions and eventually become aging systems of stars still held together by gravity. On that scale, the slowing of events would not feel like a sudden loss. It would resemble the surface of a lake after the wind has begun to fade. The largest ripples disappear first, smaller motions continue to spread, and over time the water becomes smoother. The matter is still there, only the rhythm of change has become different. And within that deepening quiet, the question of the final star becomes more subtle. We are no longer searching for a single lamp standing alone within the entire universe, because there may never be a viewpoint from which such a thing could be known. A more meaningful question is to ask about the final source of light within a connected region of space, where stars and remnants still belong to the same gravitational island. As galaxies grow older, the space between them will also continue to change. Distant regions may move farther and farther apart. Light may require ever more time to cross the growing distances, and one day some places may lie beyond one another's observable reach. By then, each island of galaxies may carry its own history, its own final stars, and a sky unlike the sky seen from any other island. To understand more clearly what a final star truly means, we may need to leave behind the familiar clouds of gas for a while and widen our view to see how galaxies are connected, how the space between them changes, and why a source of light described as the last may sometimes be the last only within the region we are still able to observe. In the distant future, if an observer were standing on a planet orbiting a small star, the sky above them might look entirely unlike any sky humanity has ever known. The familiar luminous band of the Milky Way would no longer stretch across the night. Distant galaxies would no longer appear as countless faint smudges in a telescope's field of view, and there would be no sense that vast structures continued outward in every direction. Most of the sky might be nothing more than a deep, remarkably uniform darkness, while every visible source of light belonged to the same region of matter that had remained together across immense spans of time. That observer might still see a few small stars. They might recognize faint remnants, cooling objects, and scattered red sources separated by enormous distances. But if they aimed a telescope beyond the edge of their local galactic system, they might find no other galaxies at all, even though those galaxies had not necessarily disappeared from the universe. They would simply no longer be able to send new light to the place where the observer stood. This is what makes the idea of the final star more subtle than it first appears. A star might be the last source of light in the sky of one region of the universe, while stars in other, unimaginably distant regions continued living out their own separate lives. There is no observer positioned outside the entire universe who could see every source of light at once, and no universal clock that could announce the moment when every region entered the same state. Each region would carry its own history, like islands that had drifted so far apart that the lights from one shore could no longer cross the distance between them. In the present era, the sky still allows us to see many such islands. Through telescopes, distant galaxies appear in countless forms: spirals with luminous arms, elliptical galaxies with soft and even light, small galaxies without clearly defined structures, and groups of galaxies interacting or slowly drawing closer together. Their light traveled through space for millions or billions of years before reaching Earth. The farther we look, the deeper we look into the past. A galaxy 1 billion light-years away does not appear as it exists now, but as it existed 1 billion years ago. Light is a remarkably patient messenger, but it cannot deliver information instantly. Every image in the sky is an image from the past, whether it is only a few years old or comes from nearly the earliest ages of the universe. In the future, this connection through light between distant regions will become increasingly difficult to maintain because the space between large structures continues to expand. This expansion does not stretch individual planets or stars apart. Smaller systems held tightly together by natural forces are not simply pulled open by the growth of space. Gravity still keeps the moon orbiting Earth, Earth orbiting the sun, and stars moving within galaxies. cosmic expansion becomes apparent across much greater distances, between groups of galaxies that are not gravitationally bound to one another. There, distances can increase as space itself continues to change. A galaxy does not necessarily have to move through space at an ever greater speed in the way an accelerating spacecraft would. Instead, the space between two galaxies grows larger. We might imagine two leaves floating on a very broad surface of water. If the water between them stretches and spreads outward, the leaves will move farther apart, even if each one is drifting only gently within the water around it. This image does not fully describe the geometry of the universe, but it suggests one important idea. Distance can increase without every object being pushed away by some invisible wind. Within a gravitationally bound group of galaxies, gravity can still keep its members close together. The Milky Way lies within such a region, along with Andromeda, the Triangulum Galaxy, and many smaller dwarf galaxies. Together, they form the local group, a system spanning millions of light-years, but still bound strongly enough that the general expansion of the universe will not carry its members infinitely far apart. Over time, the galaxies within this group may approach one another, interact, and change shape. Some may merge, while others may be stretched or absorbed into larger structures. After many transformations, the entire local region may become one old, broad, and complex galactic system containing matter that once belonged to many separate galaxies. For the stars within that system, it would still remain a shared gravitational home. They would continue moving along their orbits, passing through regions of different density and interacting with nearby objects. Even as the rest of the universe moved farther away, the local island would preserve its own internal structure. Beyond that island, other groups of galaxies might continue to exist in much the same way. Each group would remain gravitationally bound within itself. While the distances between groups expanded, the islands would not disappear. They would simply become more widely separated until the exchange of new light between them was no longer possible. Light from a distant galaxy would not suddenly vanish from the sky. As space expanded while the light was traveling, its wavelength would be stretched. Light that once fell within the visible range would gradually shift toward red, then into infrared, microwaves, and still longer wavelengths. The signal would become fainter, more difficult to detect, and increasingly dependent on ever more sensitive instruments. An observer would not watch a distant galaxy disappear from the sky in a single night. They would see it fade over time, like an image slowly receding into a very thin mist. Older light would continue to arrive, but light emitted at later times might never complete the journey. In cosmology, there is a boundary often called the cosmic event horizon. It is not a glowing edge or a wall at the boundary of space. It is the limit beyond which signals emitted in the future can no longer reach an observer, based on the way the universe continues to expand. If a galaxy lies beyond that boundary, light it emits late enough in its history will never reach our island, even though it continues traveling forever at the speed of light. The light is not blocked by any object. The space ahead simply expands in such a way that the destination always remains beyond the signal's reach. From that point onward, the histories of the two regions begin to separate. A star may be born in that distant galaxy. It may shine for trillions of years, change color, and eventually enter another state. Yet no new photon from those later stages will ever reach our region. For an observer here, that entire future lies beyond the sky that can be received. On the other side, another observer would experience the same thing. Our island would gradually fade from their sky. The Milky Way, Andromeda, and every local star would still exist, but their newly emitted light would no longer reach that distant region. Both regions would remain real. Both would continue to change, but neither would be able to tell the other what was happening. When this is extended across the entire universe, the image of one single final star begins to lose its original simplicity. There may be many regions that can no longer communicate with one another, and within each one, a different star may become the final source of nuclear light. No region would know whether light still remained somewhere beyond its own horizon. So it is more precise to speak not of the absolute final star in the entire universe, but of the final star within a region of the universe that remains connected by light, gravity, and physical relationships capable of passing from one place to another. This understanding does not make the subject any less beautiful. Instead, it makes the picture broader and more natural. The universe does not need to arrive at one single moment when everything changes at once. Each island may pass through the age of starlight at its own pace, shaped by the amount of gas it once contained, the number of red dwarfs it formed, the gravitational interactions it experienced, and the rare events that may still occur in the distant future. One island may have formed many small stars and preserved its light for longer. Another may have produced more massive stars, consumed its gas quickly, and become quiet sooner. In one region, two brown dwarfs may eventually meet and create a new star at an extremely late time. Somewhere else, that encounter may never happen. A small difference in history could shift the time of the final light by billions or even trillions of years. So when we imagine the final star, we do not need to place it at the center of all infinite space. We need only place it within a very old galactic island, where the surrounding objects still belong to the same gravitational system and can still exchange light with one another. That island may have passed through many mergers. Its old spiral arms no longer preserve their original shapes. Star clusters have dispersed, orbits have changed, and most of the cold gas that once formed stars has either been used or moved into states where it is far more difficult to gather again. The space between its objects is filled with countless remnants: cooling white dwarfs, tiny neutron stars, black holes, and planets that no longer receive much light. And among that population, red dwarfs still remain. At first, there may be billions of small stars continuing to shine. Over trillions of years, their numbers gradually decline as each one passes through its immensely long life. The change is far too slow to be felt across any familiar span of time. There is no particular century, no single millennium, that marks a clear transition. It is simply that after every incomprehensibly long interval, the island contains one fewer source of light. The stars do not all reach their endings at the same time, because they do not share exactly the same mass, nor were they all formed at the same moment. A slightly heavier star consumes hydrogen more quickly. A star born earlier has already traveled farther through its life. Across trillions of years, these small differences accumulate, slowly arranging the order in which each source of light leaves the age of nuclear fusion. At first, the sky may still hold millions of faint red points. Later, only thousands remain, then hundreds. The distances between them appear to grow, not necessarily because the island itself is expanding, but because so many sources of light have entered other states. A star may shine into an enormous region of space with no other active star nearby. Its photons continue traveling through areas filled with remnants and cold objects, carrying evidence that nuclear fusion still survives somewhere within the island. When only a few stars remain, determining which one will last the longest is still not entirely simple. The lightest star will usually have the longest natural lifetime, but a slightly heavier star may have formed much later. One small star may be thrown away from the central region of the galaxy after a gravitational encounter, while another remains. In a binary system, two objects may alter the course of each other's lives. Across spans of time this vast, even events with very low probabilities must be considered. A star may pass too close to a compact object. Two stellar systems may exchange members. A red dwarf may be drawn into a binary system or gain material from a companion. Orbits may change after countless weak interactions accumulate over time. For this reason, science cannot point to one particular star alive today and say with certainty that it will become the final source of starlight. We can only describe the characteristics that are most likely to belong to the star that preserves its light the longest. It will probably have a low mass because low mass allows fusion to proceed slowly. It must be heavy enough to continue converting hydrogen into helium, but not so massive that it consumes its fuel quickly. If it forms late, it has a greater chance of remaining after older stars have faded. And if it avoids powerful interactions throughout its life, it may continue evolving along something close to the natural path predicted by stellar models. Yet none of these qualities would allow the star to know that it was the last. Its rhythm of light would not change simply because the number of surrounding stars had declined. Its core would continue maintaining a temperature determined by its own mass and composition. Convective currents would still carry matter through its interior. Hydrogen would still be converted into helium at an extremely slow pace. Energy would still take time to travel from the deep interior to the surface before escaping into space as light. If a planetary system still surrounded it, those planets would continue along their orbits. A nearby planet might receive its reddish-orange light. More distant worlds would be touched by only a very small amount of energy. Frozen bodies might drift through broad orbits, quietly passing through seasons governed by their own long cycles. The star would not become an unusual source of light simply because the sky had grown sparse. It would be the sky itself that had changed. In its early life, the star may have formed among many others. Light from larger stars may once have flooded the surrounding region. The galaxy may have held young clusters, clouds of gas, and newly formed objects. Over time, each of those scenes would slowly pass into another state, while the small star continued its quiet work. There may never be a clear moment when it becomes the final star. Before that, two sources of light remain. One of them gradually leaves its fusion-powered phase, but its older light still needs time to cross the galaxy. From one location, an observer would continue seeing the past image of a star that had already changed. From somewhere closer, that change would have been recognized sooner. Even within the same island, the final moment would depend on location and on the time required for light to travel. If the final star were 1 million light-years from an observer, they would know that it was still shining only from light that had left its surface 1 million years earlier. Whatever the star was experiencing in its own local present would not yet be visible. This does not make the idea meaningless. It simply reminds us that all knowledge of the universe arrives through signals that need time to move. The universe does not display its present on a single shared surface. It sends us many layers of the past. Those layers are how we know today that galaxies were once younger, that the rate of star formation has changed, and that the universe is expanding. We do not see everything as it exists at one single moment, but from signals arriving with different ages, a larger story can be assembled. In the distant future, an observer inside an isolated island would have fewer layers of the external past left to study. Distant galaxies would have faded beyond detection, making the larger sky seem simpler. Evidence of the era, when the universe still contained many visible galaxies, might survive only in records preserved from earlier times if a civilization endured long enough to protect them. But for the final star, the disappearance of distant galaxies from the sky would have no direct effect on the workings of its core. It would remain within its own gravitational region, among objects that had stayed together. Space beyond the island might continue to expand, while gravity within it still preserved a shared structure. There is a particular kind of quiet in that image. It is not the quiet of a place where nothing remains, but the quiet of a system that has entered an extremely slow rhythm. Orbits continue, matter still moves, light is still created. Only the intervals between major changes grow longer and longer. At this point, the journey can pause for a moment and look back not by repeating what has already been said, but by placing the pieces of the question into their proper positions. The final star is unlikely to be a giant, because the most brilliant stars usually consume their fuel the fastest. It will more likely belong to the family of red dwarfs, where nuclear fusion proceeds slowly and hydrogen is used efficiently. It may also be born very late, when ordinary star formation has become rare, and its title as the last may not apply to the entire universe, but hold its clearest meaning within the gravitational island, where its light can still be seen. The original question has therefore changed slightly. We are no longer asking where, across all of reality, one single final star will exist. We are asking what such a source of light might be like when the rest of the sky within its own region has grown almost completely still. From far away, it would appear as nothing more than a reddish-orange point. But as we move closer, we can begin to imagine its size, its temperature, its surface, and the rhythm of life within it. We can wonder whether planets still orbited, what kind of sky its light might create, and how it would slowly change through the final stages of its life. Because after passing through the birth of stars, the extraordinary lifetimes of red dwarfs, the aging of galaxies, and the horizons that divide one region of the universe from another, the journey can now begin to narrow once again. There, within a galactic island that has already lived through most of its brilliant ages, the portrait of the final star begins to emerge. From a great distance, it is only a small point of light suspended in an immense expanse of space, not powerful enough to create a luminous region around itself, or illuminate enormous clouds of gas, as young stars once did in the distant past. Most of the nearby matter has become cooling remnants, dark planets, fading white dwarfs, or compact objects that emit almost no light. Amid that landscape, a reddish-orange point continues to remain, steady and exceedingly slow, as though time itself has grown thinner around it, while the flow of energy within has never quite come to an end. As we draw closer, the point of light gradually takes the form of a small, circular disk. It does not glow bright red like a burning coal, but carries a deep orange-red color, softer and more subdued than the light of the Sunday. Most of its energy is emitted in the infrared, beyond the range of human vision, so its visible appearance is even dimmer than the true amount of heat spreading into the surrounding space. Seen only in visible light, the star might appear remarkably modest, but instruments sensitive to infrared radiation would reveal a sphere still quietly releasing warmth into the darkness. Its mass might be around 1/10 that of the Sun, or slightly less, placing it just above the limit required for stable hydrogen fusion. This is a very special region on the scale of stellar mass. If the object were only slightly lighter, it might be nothing more than a brown dwarf, warm enough to glow during its early life, but unable to sustain the conversion of hydrogen into helium like a true star. If it were slightly heavier, its core temperature would rise, its reactions would become more intense, and its lifetime would begin to shorten. The final star may exist close to this delicate boundary, where gravity is just strong enough to keep the core hot, but not so strong that it forces the star to release energy too quickly. It does not possess the greatest supply of fuel or the hottest surface, yet it has nearly every condition required to preserve its light for the longest possible time. In size, it may not be much larger than Jupiter. This may sound strange, because stars are usually imagined as enormous spheres, but in low-mass objects, adding more matter does not increase the diameter by the same proportion. Gravity compresses the plasma more tightly, allowing a star dozens of times more massive than Jupiter to remain only moderately wider than the planet itself. Placed beside the Sun, the contrast would be unmistakable. The Sun would appear as a vast, brilliant sphere, while the smaller star would resemble a reddish-orange globe nearby. Its luminosity might be thousands of times lower than the Sun's, and its surface temperature would usually be only a few thousand degrees, rather than the nearly 6,000 degrees found in the Sun's glowing outer layer. Its small size does not signify weakness. It simply reveals that the star has reached a different kind of balance, one suited to its own mass. It does not need to generate an enormous amount of energy to support its outer layers, because the total mass-resisting gravitational collapse is much smaller. A gentler flow of energy is enough to keep the structure stable, allowing the star to avoid consuming hydrogen at a rapid pace. It is this state of sufficiency that enables it to endure long after larger sources of light have entered other forms. The sky around it no longer resembles that of a young galaxy. Glowing regions of gas have become rare. Massive blue stars no longer illuminate clouds of dust, and millions of young sources no longer gather into dense clusters. What remains is more widely scattered, darker, and slower to change. At very great distances, a few objects may still release faint traces of heat, but none of them sustain hydrogen fusion in the same way as this small star. A white dwarf may still retain warmth from its former life. A neutron star may emit extremely weak signals if it continues to rotate and still possesses a magnetic field. A black hole becomes clearly luminous only when matter falls into it. Most of the time, these remnants blend into the darkness, while the small star continues to produce new energy from within. It does not know that the sky has changed. It does not compare its light with the stars that once existed, nor does it carry any memory of earlier ages. Every process inside it continues according to the same laws that have governed it since its formation. Gravity draws matter toward the center. The temperature in the core sustains slow reactions, and energy from deep within continues to find its way toward the surface. Nothing about the star itself reveals that it has remained after all the others, because that title belongs not to its internal structure, but to the very late condition of the space surrounding it. Seen from the outside, the star's surface is not completely smooth or motionless. It is a moving layer of plasma, where hotter regions rise and cooler material sinks. Bright and dark patterns may appear, change shape, and dissolve, while magnetic fields bend through the plasma and occasionally create active regions. In its youth, a red dwarf may rotate rapidly, possess a powerful magnetic field, and produce flares that briefly increase its brightness. If the final star has already lived through a long portion of its existence, its rotation may have slowed, its magnetic activity may have become less frequent, and its largest flares may have gradually diminished. This calm does not mean that the surface has become still. Plasma continues to move, magnetic fields continue to change, and heat continues to flow outward. It is simply that brief disturbances no longer define the star's overall character. On a timescale of trillions of years, a flare lasting a few minutes or a few hours is no more than a tiny ripple appearing and disappearing across a vast sea. Most of the star's life passes in a state far more stable than those short moments of activity. Deeper inside, the matter becomes increasingly dense and hot. There is no solid crust marking a clear boundary between the surface and the interior. Instead, density rises gradually, pressure increases, and atoms can no longer preserve their familiar structures. Electrons separate from atomic nuclei, creating a plasma of charged particles in constant motion and interaction. In the deepest region, temperatures reach millions of degrees. Protons move rapidly, repeatedly drawing close before their electrical repulsion forces them apart again. Most encounters do not produce a reaction. Only a very small fraction come close enough for quantum effects and the strong nuclear force to allow them to combine. Each individual reaction is exceedingly rare, but the number of particles within the core is immense. Every second, enough reactions still occur to produce the flow of energy required to keep the entire star stable. For a small star, this slow rate is not a limitation to be overcome. It is the rate best suited to its existence. Nuclear fusion in the core is nothing like a flame. There is no oxygen, no smoke, and no flickering region of fire. Hydrogen is gradually transformed into helium through a chain of nuclear reactions, with a very small portion of its mass converted into energy. That energy does not escape the star immediately. It moves through the plasma, constantly changing direction, being absorbed and re-emitted many times before it approaches the surface. By the time it finally escapes into space, the light has taken on a form very different from the energy first created in the core. A photon leaving the surface may continue traveling for thousands or millions of years through the galactic island, crossing regions filled with dark planets and stellar remnants without encountering a single object. Most of those photons may never be seen by any eyes, yet they still carry evidence that nuclear fusion continues somewhere in the darkness. Within the small sphere, matter is not divided into sharply separated layers as it is in the sunday. Convective currents may pass through almost the entire structure, continually carrying plasma from deep regions toward the outside and then back again. Hydrogen that has not yet taken part in fusion is transported closer to the core, while newly formed helium is spread into other regions. This circulation is not like a river contained by banks, but more like a deep ocean of plasma, where countless masses of matter rise, sink, and blend into one another. These motions occur across many scales, from small regions near the surface to vast currents passing through a significant portion of the star. Thanks to this mixing, the composition of the star's interior changes relatively evenly. It does not quickly form a separate helium core while leaving most of its hydrogen in the outer layers. Hydrogen from many different regions is gradually given the chance to enter the places where fusion occurs, allowing a star with far less matter than the Sun to continue shining for a much longer time. This is not a deliberate act of conservation, but a natural consequence of the star's size, temperature, and the way matter transports energy within such a small body. Over billions of years, the amount of helium increases with extraordinary slowness. Across a span equal to the entire present age of the universe, the star's outward appearance may change only slightly. Even if two images were taken millions of years apart, the difference might still be difficult to detect without measurements of extreme precision. A mountain could erode away, an ocean could reshape its coastline, and entire ecosystems could emerge and disappear, while the star's average brightness remained almost unchanged. The familiar clocks of a planet are not suited to measuring such a life, because its rhythm of change becomes clear only when billions of years are placed beside one another. Slow as it may be, the transformation is still taking place. As the proportion of helium rises, the average properties of the plasma change, and the star must adjust its structure to preserve equilibrium. Some regions contract slightly, temperatures deep inside increase, and the rate of energy production gradually rises. This leads to a detail quite different from the familiar image of a lamp running out of fuel. Through much of its life, the star does not necessarily grow dimmer. Instead, it may slowly become brighter as it ages. This increase in brightness does not occur as a sudden step. There is no moment when the light abruptly shifts to a new intensity, because each change adds only the smallest amount across immense stretches of time. Only when compared with an image of itself from hundreds of billions of years earlier would the difference become easy to recognize. Its color also begins to shift as the warmer surface emits more energy at shorter wavelengths, causing the original reddish-orange glow to grow gradually paler. The star remains relatively small, but its light is no longer quite the same as it was in its youth. At a very late stage, it may enter a state that models describe as a blue dwarf. The name does not mean that the star must become a brilliant blue sphere. It refers only to a relative shift in temperature and spectrum, from a cool red star toward a hotter one that releases more light at shorter wavelengths. No naturally evolved blue dwarf has ever been observed, because the universe is still far too young. Even the oldest red dwarfs have not had enough time to consume most of their hydrogen and reach this stage. For the final star, this change in color may occur long after most nearby objects have already cooled. A reddish-orange point that once nearly blended into the darkness would gradually become brighter and paler. There would be no cloud of gas to reflect its changing light, and no cluster of young stars for comparison, only a small sphere transforming itself within an enormous region of space. The change would not form a dazzling climax. It would be more like the slow brightening of dawn, so gradual that no one could identify the exact moment when the color became different from before. If planets still orbited the star, those worlds would experience its increasing brightness across the ages. A nearby planet might grow warmer, while a more distant world that had once remained frozen could gradually receive enough energy to alter part of its surface. The region where temperatures are suitable would not remain fixed, but would slowly move outward as the star brightened. Whether a planetary system could remain intact would depend on the star's immensely long history, the way it formed, and the gravitational encounters that occurred throughout its life. If the star formed from a cloud of gas and dust, planets may have emerged from a disk of material in much the same way as they do in many other planetary systems. If it was created through a rare merger between two brown dwarfs, the surrounding environment may have been more chaotic, and any companion objects might follow orbits unlike those found in more familiar systems. Across trillions of years, the star might also pass near other objects, have its orbit altered, or be carried away from the central region of the galaxy. Such encounters are extremely rare over short periods, but when time stretches far enough, their cumulative probability also increases. The final star might lie in the outer regions of its galactic island, where objects are more thinly scattered and close encounters are less common. It may also have been pushed outward by a gravitational interaction, carrying a few planets with it on a journey through intergalactic space. If those planets orbited closely enough, the star's gravity would keep them bound while the entire system drifted through the darkness. In such a place, the sky would be remarkably simple, with the star serving as the main source of light and perhaps the only remaining source of visible nuclear energy. A planet would need to orbit very close to receive a meaningful amount of warmth. Its year might last only a few days or weeks, and at such a distance, tidal forces could synchronize the planet's rotation with its orbit, leaving one side permanently facing the light while the other remained turned toward darkness. On the day side, the star might appear almost fixed in the sky and larger than the sun appears from Earth because the planet would be much closer. On the night side, the star would never rise directly, though if the planet possessed an atmosphere, a thin band of light might linger near the horizon where illumination from the day side was scattered through the air. That is only one of many possibilities. The final star would not necessarily have planets, and the existence of planets would not imply the presence of life. No observer is required to give the scene meaning. Light would still fall across rock, ice, or empty space. Heat would still move through matter, and orbits would continue under gravity alone. Even without a single planet, the star would remain complete in its own way, needing no outside object to supply its fuel and no surface to reflect its light in order to continue existing. Nearly everything required for its long life would already be contained within it: sufficient mass, hydrogen, gravity, and a structure that allows matter to mix. This independence would distinguish it from many other sources of light in the distant future. A black hole shines brightly only when matter falls into it, while a white dwarf releases heat stored from an earlier age. The small star would still be creating new energy through nuclear fusion without needing to receive additional matter from outside. Every second, it would convert a tiny amount of hydrogen into helium. Each year, the change would be almost meaningless, and even 1,000,000 years would represent only the thinnest fraction of its entire life. But as trillions of years followed one another, the sum of those small changes would eventually transform the composition of the whole star. Hydrogen would decline, helium would increase, the internal temperature would slowly rise, and the light would gradually change color. None of this would happen suddenly, and no clear boundary would separate one state from the next. The star would move through its life as the sky changes before dawn, with every moment appearing almost identical to the one before it, even though after enough time had passed, the entire scene would be different. In the very late part of its life, the star might become significantly brighter than it was when it first formed. Its surface would be hotter, its structure more compact, and its remaining supply of hydrogen much smaller. The mixing that once gave it its greatest advantage would by then have carried nearly all of its fuel through the regions where fusion could occur. There would be no outer layer holding a vast untouched reserve of hydrogen, because most of the star's material would have taken part in this long process. Helium would no longer be concentrated only within a small core, but would make up a large proportion of the entire sphere. Text. Thanks to this mixing, the composition of the star's interior changes relatively evenly. It does not quickly form a separate helium core, while leaving most of its hydrogen in the outer layers. Hydrogen from many different regions is gradually given the chance to enter the places where fusion occurs, allowing a star with far less matter than the Sun to continue shining for a much longer time. This is not a deliberate act of conservation, but a natural consequence of the star's size, temperature, and the way matter transports energy within such a small body. Over billions of years, the amount of helium increases with extraordinary slowness. Across a span equal to the entire present age of the universe, the star's outward appearance may change only slightly. Even if two images were taken millions of years apart, the difference might still be difficult to detect without measurements of extreme precision. A mountain could erode away, an ocean could reshape its coastline, and entire ecosystems could emerge and disappear, while the star's average brightness remained almost unchanged. The familiar clocks of a planet are not suited to measuring such a life, because its rhythm of change becomes clear only when billions of years are placed beside one another. Slow as it may be, the transformation is still taking place. As the proportion of helium rises, the average properties of the plasma change, and the star must adjust its structure to preserve equilibrium. Some regions contract slightly, temperatures deep inside increase, and the rate of energy production gradually rises. This leads to a detail quite different from the familiar image of a lamp running out of fuel. Through much of its life, the star does not necessarily grow dimmer. Instead, it may slowly become brighter as it ages. This increase in brightness does not occur as a sudden step. There is no moment when the light abruptly shifts to a new intensity, because each change adds only the smallest amount across immense stretches of time. Only when compared with an image of itself from hundreds of billions of years earlier would the difference become easy to recognize. Its color also begins to shift as the warmer surface emits more energy at shorter wavelengths, causing the original reddish-orange glow to grow gradually paler. The star remains relatively small, but its light is no longer quite the same as it was in its youth. At a very late stage, it may enter a state that models describe as a blue dwarf. The name does not mean that the star must become a brilliant blue sphere. It refers only to a relative shift in temperature and spectrum, from a cool red star toward a hotter one that releases more light at shorter wavelengths. No naturally evolved blue dwarf has ever been observed, because the universe is still far too young. Even the oldest red dwarfs have not had enough time to consume most of their hydrogen and reach this stage. For the final star, this change in color may occur long after most nearby objects have already cooled. A reddish-orange point that once nearly blended into the darkness would gradually become brighter and paler. There would be no cloud of gas to reflect its changing light and no cluster of young stars for comparison. Only a small sphere transforming itself within an enormous region of space. The change would not form a dazzling climax. It would be more like the slow brightening of dawn, so gradual that no one could identify the exact moment when the color became different from before. If planets still orbited the star, those worlds would experience its increasing brightness across the ages. A nearby planet might grow warmer, while a more distant world that had once remained frozen could gradually receive enough energy to alter part of its surface. The region where temperatures are suitable would not remain fixed, but would slowly move outward as the star brightened. Whether a planetary system could remain intact would depend on the star's immensely long history, the way it formed, and the gravitational encounters that occurred throughout its life. If the star formed from a cloud of gas and dust, planets may have emerged from a disk of material in much the same way as they do in many other planetary systems. If it was created through a rare merger between two brown dwarfs, the surrounding environment may have been more chaotic, and any companion objects might follow orbits unlike those found in more familiar systems. Across trillions of years, the star might also pass near other objects, have its orbit altered, or be carried away from the central region of the galaxy. Such encounters are extremely rare over short periods, but when time stretches far enough, their cumulative probability also increases. The final star might lie in the outer regions of its galactic island, where objects are more thinly scattered and close encounters are less common. It may also have been pushed outward by a gravitational interaction, carrying a few planets with it on a journey through intergalactic space. If those planets orbited closely enough, the star's gravity would keep them bound, while the entire system drifted through the darkness. In such a place, the sky would be remarkably simple, with the star serving as the main source of light and perhaps the only remaining source of visible nuclear energy. A planet would need to orbit very close to receive a meaningful amount of warmth. Its year might last only a few days or weeks, and at such a distance, tidal forces could synchronize the planet's rotation with its orbit, leaving one side permanently facing the light, while the other remained turned toward darkness. On the day side, the star might appear almost fixed in the sky and larger than the sun appears from Earth because the planet would be much closer. On the night side, the star would never rise directly, though if the planet possessed an atmosphere, a thin band of light might linger near the horizon where illumination from the day side was scattered through the air. That is only one of many possibilities. The final star would not necessarily have planets, and the existence of planets would not imply the presence of life. No observer is required to give the scene meaning. Light would still fall across rock, ice, or empty space. Heat would still move through matter, and orbits would continue under gravity alone. Even without a single planet, the star would remain complete in its own way, needing no outside object to supply its fuel and no surface to reflect its light in order to continue existing. Nearly everything required for its long life would already be contained within it: sufficient mass, hydrogen, gravity, and a structure that allows matter to mix. This independence would distinguish it from many other sources of light in the distant future. A black hole shines brightly only when matter falls into it, while a white dwarf releases heat stored from an earlier age. The small star would still be creating new energy through nuclear fusion without needing to receive additional matter from outside. Every second, it would convert a tiny amount of hydrogen into helium. Each year, the change would be almost meaningless, and even 1,000,000 years would represent only the thinnest fraction of its entire life. But as trillions of years followed one another, the sum of those small changes would eventually transform the composition of the whole star. Hydrogen would decline, helium would increase, the internal temperature would slowly rise, and the light would gradually change color. None of this would happen suddenly, and no clear boundary would separate one state from the next. The star would move through its life as the sky changes before dawn, with every moment appearing almost identical to the one before it. Even though after enough time had passed, the entire scene would be different. In the very late part of its life, the star might become significantly brighter than it was when it first formed. Its surface would be hotter, its structure more compact, and its remaining supply of hydrogen much smaller. The mixing that once gave it its greatest advantage would by then have carried nearly all of its fuel through the regions where fusion could occur. There would be no outer layer holding a vast untouched reserve of hydrogen, because most of the star's material would have taken part in this long process. Helium would no longer be concentrated only within a small core, but would make up a large proportion of the entire sphere. Deep within that small sphere, the hydrogen that sustained one of the longest lives the universe can produce is approaching the final stage of its transformation. This does not happen at one clearly defined moment, because nuclear fusion does not behave like a lamp that can be switched on and off with a single motion. As hydrogen becomes scarcer, the number of reactions occurring over any given span of time gradually changes. Energy is no longer produced at exactly the same rate, while the structure of the star continually adjusts in search of a new equilibrium. For a very long time, these adjustments remain so slight that the light outside still appears steady. Only deep within has the composition of matter changed almost completely from the star's earliest days, when most of the sphere was still hydrogen and the first reactions had only just begun to produce light. Helium now makes up most of the star's mass. It is not concentrated entirely within a small core surrounded by a vast reserve of hydrogen, because convection extending through nearly the whole structure has continuously mixed the material throughout the star's life. Hydrogen from the outer regions has been carried downward, while newly formed helium has been distributed elsewhere. After trillions of years, this advantage has allowed the star to use almost all of its accessible fuel, but it also means that no large reserve remains far from the fusion region to replenish it as before. The final traces of hydrogen are spread more thinly through a sphere increasingly rich in helium. They still take part in fusion whenever they pass through regions hot enough, but their contribution to the star's energy becomes smaller and smaller compared with the total mass held together by gravity. As the flow of energy from fusion declines, the pressure supporting the star's layers also begins to change. Gravity has never stopped pulling every part of the star toward the center, and throughout most of its life, thermal energy and the motion of plasma have balanced that inward pull. Now, as new energy is no longer supplied at the same rate, the star begins to contract slightly. This contraction releases gravitational energy, heating the material inside and temporarily helping the star remain luminous. So even after its hydrogen supply has fallen sharply, the star does not immediately grow darker. Some of its light now comes from the gradual shrinking of its own structure, as matter slowly converts part of its gravitational energy into heat while moving toward a denser state. The contraction creates an extremely slow cycle of adjustment. As the central region becomes denser and hotter, the remaining hydrogen may fuse a little more rapidly, adding energy and slowing the contraction. As the hydrogen continues to decline, fusion weakens again, allowing gravity to draw the material closer together. The star passes through many small steps like these, none sudden enough to become a distinct event on its own. Across spans of time longer than the universe's present age, its size, temperature, and brightness change along a continuous path, with each new state differing only slightly from the one before it. In more massive stars, contraction after the decline of core hydrogen can raise the temperature high enough for helium fusion to begin. 3 helium nuclei can combine to form carbon, opening a new stage and allowing the star to continue producing energy from a different kind of fuel. But the final star imagined here is too small to follow that path. Its low mass allowed it to live for so long, but it also limits the pressure and temperature its central region can reach. Even as the star contracts and becomes hotter than it was in its youth, its core never reaches the conditions required to sustain the large-scale conversion of helium into carbon. Helium, therefore, does not become a new source of fuel. It accumulates as the product of a fusion-powered life that has lasted for an extraordinary length of time, eventually forming most of the remaining matter. But it cannot continue the chain of reactions in the way hydrogen once did. This is the natural limit imposed by the same low mass that gave the star its exceptional longevity. If it were larger, it might enter new stages of fusion, but it would also live more quickly. Because it is small enough to endure the longest, it is also unable to travel much farther along the path of creating heavier elements. The star does not expand into an enormous sphere like stars, with masses closer to that of the Sunday. There is no vast envelope driven far outward, no surface swelling enough to engulf the orbits of nearby planets, and no clearly defined red giant phase like the one found in the lives of larger stars. Its deeply mixed structure allowed it to use hydrogen along a different path, so its ending is gentler as well. The star retains most of its matter and slowly contracts as hydrogen fusion fades, requiring no dramatic event to mark the transition. If planets still orbit it, they may experience this change as a process unfolding across countless ages. During the period when the star grows hotter and brighter, nearby planets receive more energy, while the region of relatively moderate temperatures gradually moves outward. Later, when fusion truly begins to decline, and the star leaves its stable luminous state, the amount of energy reaching those planets changes in the opposite direction. There is no final day when the light remains exactly as it was before and then suddenly disappears. Each era is only slightly brighter or dimmer than the one before it, allowing planetary climates and surfaces to adjust gradually, if those worlds still exist. Deep inside the star, the last hydrogen reactions continue wherever enough fuel and heat remain. A proton may pass through countless collisions before finally taking part in a reaction. A small region of plasma may be carried downward by convection, release a little more energy, and then blend back into the helium-rich structure. The number of reactions is still enormous by any familiar measure, but compared with the star's long stable era, they have become increasingly sparse within the rhythm of its own life. Light continues to leave the surface. Photons produced during this final stage may take a long time to move through the plasma, repeatedly changing direction and energy before escaping. Once they enter space, they carry no obvious mark identifying them as products of the final reactions. They simply continue traveling like every photon that left the star before them, crossing vast regions, reflecting from a planet if they encounter one, or drifting outward into nearly unobstructed space. There is no final photon that could easily be recognized from the outside, because even after nuclear fusion has nearly stopped, the star still retains an enormous amount of heat. It can continue radiating energy stored within its matter, released through contraction and through the gradual cooling of its dense structure. So the end of new energy production through fusion does not mean that the surface immediately becomes dark. The transition between an active star and a hot remnant is continuous, with no sharp boundary visible to the eye. As thermal pressure ceases to play the main role in resisting gravity, the matter is compressed into a smaller volume. Electrons within the plasma are forced so close together that a quantum rule becomes important. Electrons cannot occupy identical states, so when matter is compressed strongly enough, they create a form of pressure that does not depend entirely on temperature. This is known as electron degeneracy pressure, and it can prevent the material from collapsing further even when nuclear fusion no longer supplies energy as it once did. This is not a new force arriving from outside. It is a consequence of the way quantum particles are allowed to arrange themselves within extremely dense matter. As more and more electrons are forced into a confined space, they must occupy states with higher momentum, creating resistance to further compression. Gravity continues pulling inward. Degeneracy pressure pushes back against that tendency, and a new equilibrium gradually forms. The sphere that was once a red dwarf contracts into an object far smaller than before. Its final size depends on its mass, temperature, and the amount of matter it retains, but it may be only a few times the size of Earth, while still carrying a significant fraction of the Sun's mass. The material inside is so dense that a small volume can contain far more mass than any ordinary substance found on the surface of a rocky planet. This remnant is composed mainly of helium because the star never reached the conditions required to transform helium into carbon. It is known as a helium-white dwarf, although its initial light may not appear purely white to human eyes. Its color depends on its surface temperature, and soon after forming, the remnant may be extremely hot, releasing much of its light at shorter wavelengths. Over time, as heat escapes, both its color and brightness continue to change. The name white dwarf does not mean that it is still a star producing energy through nuclear fusion. It is the hot, dense core left behind after that process has nearly ended. Its light comes mainly from heat stored within the material, like an object that was once heated intensely and is now slowly releasing its energy into the surrounding environment. No large fuel source continues replenishing that heat from within, but the initial temperature is enormous and the remnant is extremely dense, so the cooling process may still continue across immense stretches of time. For a while, the outer layer of the helium-white dwarf may still contain a very thin amount of hydrogen. Under suitable conditions, that hydrogen may continue participating in weak reactions and extend the remnant's period of luminosity. But this is no longer the stable phase of a deeply mixed red dwarf. The object's structure has changed. Most of its mass is now helium, and the small amount of newly produced energy plays an ever-diminishing role compared with the heat escaping from the remnant as a whole. If this process were viewed at a greatly accelerated pace, the star's surface might seem to contract and change color as its light shifted from being sustained by nuclear fusion to being powered mainly by residual heat. But at the universe's true pace, every change takes an immense amount of time. There is no rapid collapse, no layer of matter falling inward within minutes, and no sudden flash marking the moment of transition. The small star gradually enters a denser state, with each layer of matter adjusting and each region changing in temperature until degeneracy pressure stabilizes the structure. Throughout this process, light continues to spread outward, though its energy spectrum slowly changes with time. Unlike a massive star, this object does not end in a supernova. Its gravity is not strong enough to force the core to collapse into a neutron star or a black hole. Nor does it pass through a sequence of reactions that creates many layers of heavy elements before a great explosion. Nearly its entire life has revolved around the conversion of hydrogen into helium, proceeding so slowly that no massive star could sustain the process for nearly as long. The ending, therefore, reflects the beginning. A life that began gently within a small cloud of gas also enters its new state without a brilliant event. The star that was once difficult to see among billions of other sources ends its fusion-powered phase through a process as quiet as the life it lived. If a planet still orbits it, the planet's sky continues to change. The central source of light contracts, its color and energy shift, and the total amount of heat received gradually declines after the final period of increasing brightness. A world that once lay within a warm region may begin to cool. Its atmosphere may condense, its oceans may freeze, and its surface may slowly lose the cycles that once depended on the star's energy. These changes do not need to occur all at once. The layers of an atmosphere respond at one pace, the oceans at another, while the deep interior of a planet may retain its own heat for much longer. Even as the light of the white dwarf weakens, geological energy, tidal forces, or stored heat may continue sustaining small processes for a time. The space around the star does not pass immediately from a state of illumination into complete stillness. If there are no planets, the helium white dwarf continues cooling in the same way. Its surface emits photons that carry heat away, while the interior gradually becomes colder. Because stable nuclear fusion no longer replaces the energy being lost, every escaping photon reduces the total heat inside by an exceedingly small amount. At first, the white dwarf may still appear brighter at certain wavelengths than the red dwarf that once existed, because its surface temperature is high even though its size has become much smaller. But this light is not enduring in the same sense. It is not sustained by a supply of fuel capable of lasting for trillions of years. It is the light of heat, leaving an object that has completed the main part of its nuclear life. Over time, the surface cools, the spectrum gradually shifts toward longer wavelengths, and the luminosity declines. Inside, helium ions may arrange themselves into more orderly structures once the temperature falls far enough, causing the matter to enter a state resembling an extraordinarily dense crystal lattice. Electrons continue producing the pressure that keeps the object stable, while the helium nuclei vibrate more and more weakly around their equilibrium positions. The remnant no longer contains a hot core producing new energy, but it is not yet a completely cold object. An enormous amount of heat remains stored within its structure and requires a very long time to escape. Within the aging galactic island, it may remain one of the brighter objects against the surrounding darkness, even though its light is only the lingering remainder of a life that began unimaginably long ago. This is why the phrase, "the final star stops shining," must be understood slowly. Nuclear fusion may end first, while thermal light continues. Visible light then fades, even as infrared radiation is still emitted. Much later, even that heat becomes extremely weak. But there is no simple moment when every form of energy disappears at once. The universe does not change states with a switch. It changes along long curves, where one process gradually declines while another continues, and the boundary between two eras becomes clear only when viewed from a sufficiently distant point in time. The helium white dwarf still contains nearly all the matter that once formed the final star. Hydrogen nuclei passed through chains of reactions, became helium, and released energy into space. That light has already traveled away, perhaps so far that it no longer has any connection with the object that created it. Other photons continue escaping from the remnant's surface, carrying away heat left behind by contraction and by the long history of the matter within. Nothing that once existed has vanished completely. Matter has changed state, energy has dispersed, and the structure has contracted. The star is no longer a sphere of plasma supported mainly by heat from nuclear reactions, but its mass remains, held within a small, dense, and enduring object. From a distance, an imagined observer might see the point that once glowed reddish-orange become pale white and then slowly fade. If images of the earlier star had been preserved, the two stages might appear to belong to entirely different objects. First, a broader, cooler red sphere that endured through most of its life, and then a small, hot, dense remnant. Between them there was no explosion, only a transition so prolonged that every individual moment seemed ordinary. In a region of the universe where no other star still sustains nuclear fusion, this change marks the end of the age of starlight in its deepest sense. The flow of new energy once created by combining light nuclei no longer continues as steadily as before. Light remains, but it now comes from stored heat, from objects gradually cooling, and from rare events that may still occur among the remnants. The final star has not disappeared. It has simply ceased to be a star in the nuclear sense and become a helium remnant slowly releasing the heat that remains. Around it, orbits may continue. Dark planets may still move. The white dwarf remains held in shape by its internal pressure, and photons leave its surface at an ever-decreasing rate. The galactic island has not become completely inactive. It has merely entered an era in which light is no longer sustained by stellar cores, converting hydrogen into helium. From here, the sky does not immediately become completely dark. Other white dwarfs still retain heat. Neutron stars, black holes, and compact objects continue to exist. Rare encounters may create brief flashes of light, while faint radiation continues traveling through space. But the steady flow of light that once came from stars has reached its final stage. Where a small star once lived for trillions of years, a helium white dwarf now remains smaller, denser, and still surrounded by an exceedingly faint glow. It no longer creates a new day for the worlds around it as it once did, but neither has it fully merged with the darkness. The final light of nuclear fusion has faded. The remaining heat continues to escape, slowly and steadily, opening a new era of the universe in which stars are no longer the primary sources of light, yet matter still has many long stories that have not reached their end. Where a small star once lived for trillions of years, a helium white dwarf now remains smaller, denser, and still surrounded by an exceedingly faint glow. It no longer creates a new day for the worlds around it as it once did, but neither has it fully merged into the darkness. Its remaining heat continues to escape, slowly and steadily, opening a new era of the universe in which stars are no longer the primary sources of light, yet matter has not ceased to move. At first glance, this change may seem like the end of all activity. Once no stellar cores remain to convert hydrogen into helium, the steady sources of light that once shone across galaxies gradually disappear. But a universe without active stars is not an empty universe. What the stars created still remains in many different forms: white dwarfs, neutron stars, black holes, planets, brown dwarfs, asteroids, dust, and extremely thin streams of particles continuing to move through space. The age of starlight does not end like a door closing. It ends through a change in the dominant sources of energy. Before this transition, most visible light came from stars sustaining nuclear fusion. Afterward, light comes mainly from heat stored within remnants, from matter falling toward compact objects, and from rare encounters between celestial bodies that have existed for an unimaginably long time. These events no longer create a brilliant sky, but they still reveal matter responding to gravity, motion, and the laws of quantum physics. The helium white dwarf that was once the final star will continue cooling, according to a simple principle. Every photon escaping from its surface carries away a small amount of energy. During its earliest stage, the object remains hot enough to emit visible light. Later, most of its radiation shifts into the infrared, and then toward even longer wavelengths as its temperature continues to fall. This process is so slow that it is difficult to associate it with any particular moment. A white dwarf may fade across spans of time far longer than the present age of the universe. As the heat within declines, helium nuclei in the dense material may arrange themselves into a crystal lattice. Crystallization does not make the object resemble an ordinary stone, because the pressure keeping it stable still comes mainly from degenerate electrons. But its internal structure becomes more orderly, and this phase transition can release additional heat, slowing the cooling process. Even without nuclear fusion, the object has several ways of preserving its energy longer than simple intuition might suggest. Eventually, given enough time, the white dwarf will become so cold that it emits almost no significant light. Such a remnant is commonly called a black dwarf. No black dwarfs exist in the universe today, because approximately 13.8 billion years has not been long enough for any white dwarf to cool into that state. A black dwarf belongs to the far future, inferred from the way dense matter gradually loses heat across immense cosmic ages. Within an ancient galaxy, the number of dark objects like these may become enormous. White dwarfs that once shone gradually become black dwarfs. Neutron stars continue slowing their rotation. Planets lose heat from their surfaces, while their deep interiors may retain small amounts of energy for much longer. Brown dwarfs continue cooling after they are no longer warm enough to glow clearly. Most objects do not disappear. They simply become increasingly difficult to detect through light. If this galactic island were observed using vision alone, almost nothing would stand out. But if gravity could somehow be sensed directly, the landscape would still contain a great deal of structure. Remnants would continue orbiting their shared center. Binary systems would still circle one another. Planets still bound to central objects would preserve their orbits, and objects ejected from the system would continue traveling through intergalactic space at nearly constant velocities. Over time, weak gravitational interactions repeated countless times could reshape the entire structure of an aging galaxy. When two objects pass close to one another, one may gain energy and move into a wider orbit, while the other loses energy and drifts closer to the central region. After innumerable encounters, some remnants may be expelled from the galaxy and begin solitary journeys through the wider darkness. Those that remain gradually gather into a smaller, denser system. A planet that once orbited a star may have its path altered by a close encounter. It could move farther away, enter an orbit around another remnant, or be thrown out of the system entirely. Once it becomes a rogue planet, it still retains its mass, its structure, and perhaps a small amount of internal heat. Its surface receives almost no light, but radioactive processes and residual warmth deep within may continue for a very long time. Within binary systems, two white dwarfs or two neutron stars may continue losing orbital energy through gravitational waves and slowly draw closer together. Most systems will require extraordinarily long periods, while many will never merge at all. But some pairs that are close enough may eventually meet, producing luminous events within a universe that has otherwise grown very dim. A merger between compact objects can release energy briefly, creating gravitational waves, radiation, and streams of particles before the system returns to a quieter state. Black holes also continue to exist. Most of the time, an isolated black hole produces no easily detectable light. If matter passes close enough and begins to fall inward, it may heat up before crossing the event horizon, creating a brief burst of radiation. In an aging galaxy, free matter becomes scarcer and encounters become less frequent, so episodes like these grow increasingly rare. Black holes may become the objects that preserve mass the longest within large structures. Stellar mass black holes, intermediate mass black holes, and the supermassive black holes at galactic centers remain held within gravitational systems, sometimes merging when their paths bring them together. Across immense spans of time, many compact objects may fall into central black holes, increasing their mass before the surrounding environment becomes too thin to provide any significant additional material. According to our current understanding of quantum physics, black holes do not survive forever. They may emit an extremely weak form of radiation, usually called Hawking radiation, and therefore lose mass very slowly. For black holes with astronomical masses, this process takes so long that it is almost impossible to observe directly in the present era. Only in the extremely distant future, when the cosmic background has become far colder and surrounding matter far more sparse, will this loss of mass become a significant part of their evolution. A small black hole evaporates more quickly than a large one, while supermassive black holes may survive across spans of time that are difficult to express using familiar numbers. Most of their existence passes with almost no visible change. Only near the end, after their mass has declined substantially, does the evaporation rate accelerate, allowing the remaining energy to be released more rapidly. Here, the idea of darkness should not be understood as the absolute absence of radiation. Space would still contain photons with extremely long wavelengths, lightweight particles, and ancient signals from earlier eras. The cosmic background radiation would continue to stretch as the universe expanded, lowering its effective temperature. Light that once carried high energy would become weaker, more diffuse, and less likely to interact with matter. A photon, created by a star trillions of years earlier, might still continue its journey if it had never been absorbed. As space expanded, its wavelength would lengthen and its energy would decline. It would remain part of the history of light, only no longer energetic enough to produce easily noticeable effects. The universe preserves traces of its past, not as complete images, but as signals that grow increasingly faint and widely dispersed. In even more distant eras, an important question begins to arise. Are protons truly stable forever? Within the standard model of particle physics, the proton is considered stable, but some extended theories predict that it may decay after an extraordinarily long time. So far, no proton decay has been confirmed. For this reason, when looking beyond the era of black holes, science must clearly distinguish between conclusions that can be drawn with relative confidence and possibilities that still depend on unverified physics. This uncertainty does not make the picture less meaningful. It simply places an honest boundary around what is currently known. We can say with considerable confidence that stars will not shine forever. White dwarfs will cool. Gravitational systems will continue to evolve, and black holes may lose mass through quantum radiation if our present description is correct. But when time is extended across enormous powers of 10, unknown details of particle physics begin to determine the ultimate form of matter. Whichever possibility proves correct, the overall tendency remains the same. Energy becomes more widely dispersed. Hot regions gradually cool, concentrated sources of light become fewer, and temperature differences between one place and another diminish. As fewer differences remain to be used, the ability to sustain complex processes also declines. This is the foundation of the idea commonly known as the heat death of the universe, though the name can suggest a sudden event far more dramatic than what the physics actually describes. There is no moment when the universe dies, in the sense that all motion comes to an end. Particles may continue moving, space may continue expanding, and quantum fluctuations may remain part of the structure of nature. What declines is the ability to create organized flows of energy from one region to another. As everything moves closer to equilibrium, fewer opportunities remain for new structures to form and endure. That era lies so far ahead that most of the universe's history may still be waiting in the future. The final star marks only the end of a bright opening chapter, not the end of time itself. Beyond it lies the era of remnants, the era of black holes, and perhaps even more distant stages that present-day physics can describe only through models. If the entire future were compressed into a calendar, the age in which stars shine might occupy only a small portion of the earliest pages. Most of the remaining pages would belong to colder and slower states. This does not make the age of starlight unimportant. On the contrary, it reveals that we are living during an extraordinary interval when energy is still concentrated enough for galaxies to glow, planets to be warmed, and matter to organize itself into structures of remarkable complexity. The atoms within the human body were formed through the history of stars. Light allows us to observe distant galaxies and reconstruct the past of the universe. The heavy elements that make up rock, water, and air are all connected to generations of stars that lived before the Sunday. The age of starlight is not merely an era filled with bright points, but an era in which matter is continually transformed, mixed, and arranged into new structures. The helium white dwarf that was once the final star would continue to cool. For an immensely long time, it would remain a point slightly warmer than the surrounding background. Eventually, its brightness would fall until it became difficult to distinguish from other remnants. It would become a black dwarf, still possessing gravity but emitting almost no light. Any planets still traveling with it would grow colder as well, while their orbits continued without the need for a bright sky. The scene might be described as quiet, though not with the quiet of a room or a windless night. It would be the quiet of distances too great, densities too low, and changes too slow to create any clear rhythm. Every particle would still carry energy, and every photon would still move, but encounters would become so rare that most of space would contain almost no significant events. There is no need to view that future as a loss. The laws of physics do not divide time into eras that are better or worse. The young universe was dense, the stellar universe is rich with light, and the very old universe may be sparse and cold. Each era is simply the result of the one before it, connected through processes that require no outside hand to guide them. Returning to the black dwarf that was once the final star, almost no outward sign would remain that it had ever shown, but the absence of light would not erase its history. The dense helium within it would be the result of trillions of years spent converting hydrogen into helium. The heat it once released would have warmed the surrounding space. Photons that once left its surface might still be traveling somewhere far away, even though their wavelengths had been stretched and their energy had become extremely small. The universe after starlight would therefore not be a blank page. It would be more like the long remainder of a piece of music after the main notes had stopped sounding, while faint vibrations continued to spread and slowly blended into the background. No new great melody would begin, but what had already been played would still leave traces in the way energy was distributed. Seen from that distant future, the sky of today would appear even more remarkable. We live at a time when stars are still being born, when light from billions of galaxies can still reach our telescopes, when the sun remains stable enough to create the familiar rhythm of day, and when matter, on a small planet, can look back and consider its own origins. So when we think about the universe after starlight, there is no need to hurry toward the idea of an ending. What becomes clearer instead is the vastness of time, the endurance of matter, and the way each state slowly transforms into the next. The light of stars is only one part of that greater process, but it is the part unfolding around us at this very moment. The night sky is still filled with stars. Clouds of gas are still collapsing. The smallest red dwarfs have only just entered the opening portion of their lives. Distant galaxies are still sending ancient light toward Earth, and every photon received today is evidence that the age of light has not come anywhere close to its final chapter. On the time scale of the universe, it has only just begun. From cold clouds of gas drifting between the stars, gravity slowly gathered matter together, heating the central regions and beginning reactions capable of sustaining light for millions, billions, or even trillions of years. Every star is born from the same basic laws, yet mass carries each one into a very different rhythm of life. Massive stars shine intensely, consume their fuel quickly, and complete their lives while the smaller stars beside them have barely changed. Red dwarfs, faint enough that most cannot be seen with the naked eye, preserve their hydrogen longer, mix their fuel more efficiently, and become the most enduring sources of light the universe can create. Over time, galaxies also gradually change. Cold clouds of gas become less abundant, star-forming regions appear less frequently, and new generations of light are born farther and farther apart. Star formation does not stop in a single moment. It slows across countless ages until the appearance of each new star becomes a rare event within an ancient galaxy. Perhaps the final red dwarf will form from a remaining pocket of gas, or from an exceedingly rare encounter between small objects that have drifted through space for a span of time almost beyond imagination. That source of light will probably not stand at the center of the entire universe like a single lamp visible from everywhere at once. As space continues to expand, distant groups of galaxies will gradually lose the ability to exchange light, leaving each gravitational island with its own sky and its own history. The final star is therefore most clearly understood as the last source of fusion-powered light within a connected region of the universe, where its photons can still travel among the orbits, remnants, and worlds belonging to the same galactic island. For most of its life, that star may be nothing more than a small reddish-orange sphere, not much larger than Jupiter but dozens of times more massive. Inside it, hydrogen continues to become helium at an extremely slow pace, while currents of plasma mix matter throughout almost the entire structure. Billions of years pass with only the slightest change in brightness. Then trillions of years follow, as the star gradually grows hotter, brighter, and less red than it was before. There is no sudden climax, only small adjustments accumulating over time until nearly all of its hydrogen has passed through the regions where fusion can occur. When the final nuclear reactions fade, the star does not disappear, and the sky does not immediately become completely dark. The small sphere contracts into a helium-white dwarf, still holding an immense amount of heat and continuing to shine for a very long time. Its radiation then shifts gradually toward weaker and longer wavelengths, its temperature falls, and the remnant becomes increasingly difficult to detect. Farther into the future, it may become a cold, dense black dwarf, still carrying the mass and history of the star that once shone, even though it can no longer create a new day for any worlds around it. After the age of starlight, matter continues to exist. White dwarfs cool, planets travel through dark orbits, neutron stars rotate more slowly, and black holes preserve their mass across even longer spans of time. Encounters between objects become rare, concentrated light grows less common, and most of space enters an extraordinarily slow rhythm. The universe does not stop. It simply moves into states where major changes require more and more time to appear. But all of this still lies very far ahead. The universe today is only about 13.8 billion years old, while the smallest red dwarfs may continue shining for trillions of years. The longest-lived stars have not yet passed through any significant portion of their lives, and the era of cold remnants exists only within models extended from the physical laws we observe today. So when we return to the present sky, what appears is not an ending, but a universe still filled with beginnings. Clouds of gas are still collapsing within the dark regions of galaxies. Protostars are still gathering matter, New planetary systems may still be forming around newly awakened sources of light, while radiation from distant galaxies continues crossing space to bring Earth images from the deepest past. The Sun, too, remains within the stable middle portion of its life. Its light continues to cross the distance between the Sun and Earth, warming the planet's surface, moving through the atmosphere, and providing energy for countless processes unfolding around us. Every familiar morning is a small part of the age of starlight, an era that will continue far longer than any span recorded in human history. There is no need to remember every enormous number we have passed along the way, or to imagine in full the trillions of years separating the present from the final star. It is enough to keep one simple image. Within an immense universe, the source of light that remains the longest may not be the brightest one, but a small star using what it has at the slowest pace nature allows. And one day, unimaginably far away, that light will also pass into another state, as all matter in the universe is always changing. But tonight, the sky is still filled with stars. New sources of light are still being born, and the smallest stars still have almost their entire lives ahead of them. As those distant ages slowly drift from the mind, perhaps all that needs to remain is the feeling that the universe is in no hurry, and that the light around us still has a very long time. On the time scale of the universe, the age of light has only just begun.